what is a vector field on a smooth manifold. We shall discuss first these topics here, and so in particular integral curves, local flows, and then we will have a first approach with Lie brackets and definition of what a Lie algebra is. And after this first part, I shall focus on the groups and the algebras, so this will be the second part of today's lecture. And so first of all, we shall discuss the groups and moving through examples and properties of such special type of manifolds. And then we will see a related concept, which is that of the algebras. And so starting from a Lie group, we shall see that it is possible to define a certain vector space endowed with a certain operation on its vectors, which gives such a space the structure of what is called a Lie algebra. So we shall discuss these two topics here. And finally, if time permits, I shall say something about Lie group actions, which is not part of this book. And I have a further part coming from a book by Lie, which is this one here. And so if I have time, I shall discuss this part here also. And so this is the plan for today, and then in the next lecture you will start again from here, so studying differential forms again with Maurizio. Okay, so this is the plan for today, so let's start, and let me just briefly recall what is a vector field. You saw this last time. So a vector field on a smooth manifold is a section of the tangent bundle of the manifold. So this means that you defined last time the tangent bundle. It is a vector bundle that you can define over a manifold, and you say that the vector field is a section of this tangent bundle. This means that you have a map going from the manifold to the tangent bundle of the manifold, such that at each point x associates what you denote by xp, which is a tangent vector to the manifold at that point. And you require this map between smooth manifolds to be a smooth map. And last time you saw what are some equivalent conditions guaranteeing that a section of such a vector bundle is a smooth section. So today we shall focus on this second part of this chapter. So first of all, we shall see that there is a way of associating a certain curve to any vector field on a manifold. And in particular, a natural question is the following. So you have a vector field. This means that on your manifold at each point, you have a tangent vector to the manifold at that point. And then you ask whether there exists a curve on the manifold whose tangent vector at each point is precisely the vector belonging to the vector field at that point. So this will be the first problem we shall discuss today, and we shall see that it is closely related to the study of some ODEs problems. So analysis comes into play here today. And then after this, we shall see how to introduce an operation on vector fields, which is this bracket operation, that gives the space of all smooth vector fields on the manifold the structure of what is called a Lie algebra. And so we shall see for the first time here what is a Lie algebra, and then we shall discuss more properties regarding the algebras later on. And then finally, in this chapter, we shall discuss this notion of related vector fields. So if you remember last time, you said that if you have a smooth map between manifolds, then you can consider its differential, which is a map between tangent spaces of the two manifolds. It is a linear map. And so with this differential, you can map a tangent vector to the first manifold into a tangent vector of the second manifold. So let's say you have your map here between manifolds. You choose a point P of M, and you take the differential, which is a linear map from the tangent space at M of M at P to the tangent space at M at Fp. So in this way, you can associate to a tangent vector here, a tangent vector here. And so the question is whether we can do something similar also with vector fields. And we shall see that it is not always possible, but there is some, let's say, convenient definition that one can consider. And in some setting, it is possible to do this. Okay, so this part here was discussed last time, so I will skip this, and I will go directly to the first topic of today, which are the integral curves. So let's start with the definition. So we have a vector field, a smooth vector field on a manifold. So the picture you might want to have in mind is kind of this. So you have the manifold here, and at each point you have a tangent vector to the manifold at that point. And so you have this family that depends smoothly on the point you are considering. And so the question you ask is whether there exists a curve on the manifold whose tangent vector at each time is precisely the value that this vector field takes at that point. So what you're asking is whether there exists a curve on your manifold such that at each time, at each point, its tangent vector is precisely the vector corresponding to the vector field at that point. So if such a curve exists, you call this an integral curve of the vector field X. And so this is completely determined by this condition here. And moreover, so as you can see, you consider an open interval where your curve is defined. And usually you assume that it contains 0, and you consider a starting point for your curve. So you consider a point on your manifold, and you require your curve to start at time equal to 0 from that point. So this will be what we. So this will be the integral curve of a smooth vector field on a manifold. And in order to emphasize the dependence on the initial point, sometimes one denotes the integral curve by specifying also the point together with the time, so together with the real parameter that lets the curve move. And moreover, you define an integral curve to be maximal if its domain cannot be extended to a larger interval. So it means that once you consider an integral curve, you can define it on some open interval, and eventually you can extend this open interval to a larger interval. But in some cases, you will end up without having the whole real line, the whole real numbers. So in that case, consider the maximal possible interval you have, and you define an integral curve to be maximal if its domain is maximal in this sense. So let's start with examining an example of an integral curve of a vector field. And in particular, here there is a vector field you already met during the last lecture. And this is the vector field associating to each point of the space R2, this vector here. So you may imagine this as something like this. So here we have R2. And then at each point, so for instance, at the point once you want to look for the integral curve of x starting at the point 1, 0. So we start, let's say, from here. The tangent vector at that point, if you replace y and x with 0 and 1 here, you will get the vector 1, 0. And so here we have this vector here. And so, of course, choose other points and you will find other vectors belonging to this vector field, and so on. And so you require, okay, let's start from here. We want to find an integral curve for the vector field x starting from here. So what we want is that this curve which will be a curve given in this way. So we have two real valued functions depending on t. We want this to be a curve whose tangent field is precisely the vector field evaluated at c. So this means that we want the derivative of c, which is given by x prime and y prime, equals the vector field evaluated at ct. So this means that we want minus yt xt here. So as you can see, what we end up with is a system of first order ordinary differential equations. We want to solve this system of equations under this initial condition. So we have what is called a Cauchy problem. So these two together with this condition here give you the so-called Cauchy problem. And here you can use some standard results of analysis. First of all, to just notice that as y equals minus the time derivative of x, from this, by differentiating, you get that the time derivative of y is minus the second derivative of x. And replacing this equation in the second one here, what you end up with is this second order ODE for the function x. And this might be kind of familiar, probably you've already met such type of equation. This is an example of the differential equation associated with the so-called harmonic oscillator. So in general, you have some non-zero real number omega, and this second order differential equation is what is the differential equation for the so-called harmonic oscillator. And solutions of such an equations are well known, and in particular, if you want to solve this one, you will end up with a solution of this form. So your x will be some constant times the cosine of t plus some other constant times the sine of t. You can differentiate x and recall that y and the derivative of x are related by this identity here, by this equation here, and get the expression y. So once you have this general integral for this Cauchy problem, what you can do is to impose the initial condition, and this will give you a unique solution to this problem. And in particular, requiring that x at time 0 equals 1 will give you that a has to be equal to 1. And requiring that y at time 0 equals 0 will tell you that b at time 0 will be, it will tell you that b will be 0. So in particular, what you end up with is that the integral curve of this vector field here that we are considering, starting at the point 1, 0 here, is nothing other than the parameterization of the unit circle. And so this picture here is taken from a previous page of this book, and this is precisely what's going on. So let's assume that this point here is the point 1, 0, and so what we found is precisely this circle here. And as you can see, this is the vector field we are considering along points of this circle. And of course, this is what's going on if you consider the starting point 1, 0. Of course, you can consider any other point where you want to make your flow start. And in particular, if you consider a point with generic coordinates x naught and y naught, then what you will obtain, again, using this form for the solution, is that a has to be equal to x naught and b has to be equal to minus y naught. And so in particular, the solution to the system of ODEs we are considering as this form here, it is defined for every real time. And as you can see from here, you can also rewrite this using this matrix notation. So you can consider this matrix and multiply it by the vector, the column vector with the initial data you are considering. And maybe you have already met, or almost for sure you have already met a matrix like this one. This is the matrix representing a rotation in the two-dimensional plane, a rotation of angle equal to t. And in fact, what we have just shown with this discussion is that the integral curve of the vector field we are considering starting at a point P can be obtained by rotating the point counterclockwise about the origin through an angle t. So this map here, this matrix here, represents precisely the transformation that rotates your point in the space or in the two-dimensional space through an angle t. And moreover, we have some interesting properties of this map, which starting from this time are telling us some information of a general pattern. So what we can observe is that if we compose if we consider the integral curve starting at P until a time t, and then we consider another integral curve starting at, let's say, C of t of P, then composing these two is the same of considering the curve starting at P at time s plus t. And this is because, just because if you just have to multiply the matrix representations if you want and apply some properties of sine and cosine function to just recognize that the transformation associated with rotating first by an angle of t and then by an angle of s is just the transformation that rotates the point by an angle of s plus t. So we are just composing these two transformations. And moreover, it is immediate from here. This is not written here, but of course you can observe that at time 0, we are not moving. So at time 0, we are staying where we started. And so in particular, from this observation here and this one here, what you get is that this map C of t, which can be seen for each fixed time t as a map going from R2 to R2, is a diffeomorphism between R2 and itself with inverse, which is given by C of minus t. And this is just because if you compose C of t with C of minus t, you will get C of t minus t because of this relation. And so this would be C0, which is just the identity because of this fact here. So in particular, what's going on here is that for each time, first of all, the integral curve is defined for each time. And we shall see shortly that this is not always the case. But it is in this case, it is defined for every real time. And moreover, you can think of this as a map C going from R to the set of diffeomorphisms of R2 in this case. And in particular, this is a special map because in some sense preserves the group structure that you have on R and the group structure that you have on the space of diffeomorphisms of R2 in this case. And in fact, more generally, this is an instance of what is called a one-parameter group of diffeomorphisms of a manifold. So in the general case, once you have a smooth manifold, you can consider the so-called group of diffeomorphisms of the manifold, which are just smooth diffeomorphisms of n with the group operation, which is composition of smooth maps. I shall say something more in detail in a while. And then what you get is that if you have a group homomorphism between the group R considered as a group with respect to the addition of real numbers and the group of the diffeomorphisms of the manifold considered as a group with respect to the composition of smooth maps, then such an homomorphism is called a one-parameter group of diffeomorphisms of the manifold. So what we obtain here is an instance of this more general object. But before going on, let's just recall some definitions on this around this definition here. So first of all, you already met this definition last time. Let me recall this. What is a group? So a group is a set, which I shall denote with capital G, with a binary operation, considering two elements of the group and giving you a third element of the group. And such an operation has to satisfy these three axioms. So first of all, you want this operation to be associative. Then you want the existence of a neutral element for this operation. This means that you have this element on your group, also on your set, which is the neutral element for this operation here. So this means that if you consider any element A in your group and you multiply it by this neutral element, you get the element A, and this does not depend on multiplying it on the left or on the right. And moreover, you want that for each element of the group there exists another element of the group, let's call it A prime for the moment, which multiplied by the element A gives you the neutral element. And you can show this if such an element is unique, and you will denote this with the usual notation A to the minus 1. So these are the three properties, the three axioms you require on this binary operation in order to have a group structure on a certain set. And so some instances of the substructure are, for instance, the real numbers with the sum, or also the integers with the sum, or for instance also the real numbers without the zero together with the product, and again the complex numbers without the zero together with the product. And what is a group homomorphism between two groups is just a map between the two groups that preserves the operation that you have on the group. So here we will have a product on G, we will have a product on H, which are two groups. And so you call a map between these two groups a group homomorphism if it preserves the group structure. It means that if you consider the image of the product of two objects in G, then you will end up with the product of the images of the two elements in H. In particular, from this definition, it follows that every group homomorphism maps the identity, the neutral element of the first group into the neutral element of the second group, and moreover that the image of the inverse of an element of the group is the inverse of the image of that element. So we shall use this definition also later when we will meet the Lie groups, but let's recall it starting from here. So what does this, let's say, algebraic, this abstract structure, what has it to do with what we saw just a while ago? Well, in the case we are considering, for instance, the set of diffeomorphisms of the manifold is a group with respect to the composition of smooth maps. So this means that you will have smooth maps from the manifold to itself, which are diffeomorphisms, so they have a smooth inverse, and you compose them and you will get another diffeomorphism of the manifold. We consider R as a group with respect to the sum, and what is a one-parameter group of diffeomorphisms according to the definition we gave before is just a homomorphism between this group here and this group here. So this means that for each t you take in R, you will get C of t, which will be a diffeomorphism of the manifold, and in particular it will satisfy the properties, the general properties we have just mentioned here. So for instance, the at time 0, it will give you the identity of between the manifold and itself, which is the neutral element for the composition of smooth maps of diffeomorphisms in the manifold. If you consider C evaluated at time s plus t, you will get the composition of the corresponding diffeomorphisms, and this is just what we wrote here for the general case. Here we are considering the plus as an operation on R and the composition as an operation on the set, on the space of diffeomorphisms. And finally, when you consider your map, your homomorphism at minus t, you will get the inverse diffeomorphism on the manifold. So these are the properties of this one parameter group of diffeomorphism of a manifold. And this is the general definition, which, as you can see, is a special case of a more general one that you can define between two groups. But as I said, of course, we are not always so lucky. So it may happen that when you consider a vector field, the corresponding integral curve, and so the flow that eventually you will define from that will not be defined for all real times. And in particular, here we have an example which is given by this vector field on the real line. So if you consider this vector field having this shape on the real line, which is just x squared times d over dx, and you want to look for the maximal integral curve starting at x equal 2, then again, you say, okay, let's start considering a generic curve x of t, and let us require that its tangent vector is precisely the vector field x evaluated at the point x of t. So again, you saw last time how to obtain a derivative of such a curve. It will be nothing but the derivative of x times the vector field spanning the tangent space at R, and this will be equal to x squared d over dx, which is just x evaluated, the vector field capital X evaluated at the point x of t. So the ODE you will get here is x dot equal x squared. So you have to solve this ODE here with this initial condition. So you want that at time 0 you start at the point 2. So this is again a Cauchy problem. And again, you can use the tools that one studies in analysis to solve such, first of all, such an ODE. And so, for instance, you can use separation of variables here, and so write this equation here as dx over x squared equal dt. Then you will integrate, and then you will use this initial condition. And what you will end up with is such an equation. So you will get that the integral of 1 over x squared is minus 1 over x, and the integral of dt will be t plus some constant c. And starting from this, you can rewrite everything in terms of x, so make the expression of x explicit. And then c is now a constant. You want to determine c, and it is uniquely determined by the initial condition we are giving. In such a case, the initial condition requires this curve at time 0 to be equal to 2, and this will imply that this capital C equals minus 1/2. And so the integral curve we have, x of t, is this one here. So it's 2 over 1 minus 2t. And the point here is that this is not defined anymore on the whole real line, but it will stop at 1/2. So the idea is that at 1/2 we have some kind of barrier that will prevent us to go further. So let's say that here we are 1/2. We started at x at 0 equal to 2. So this is not in scale, sorry for this. And you will end up with your integral curve, which is this one. So it is not defined on the whole real line. It is defined on an interval contained in the whole real line. So at the end of the day, what we have seen from these two examples is that sometimes you may obtain a solution of the flow, so a solution of an integral curve that is defined for every real time and that has some nice properties because you can treat it using the language of groups, for instance. Some other times we are not so lucky, and it may happen that the integral curve we are considering is not defined on the whole real line. But as we will see, it is possible to do some local consideration, again, using the definition of group homomorphisms we met before. And this is what led us to the next topic, which are local flows of vector fields. So we saw what's going on some examples. And of course, in general, one may ask, okay, let's start with a smooth manifold. Let's consider a vector field on the smooth manifold. I want to study this problem of the existence of integral curves in greater generality. So this means that I have my vector field and I want to look for an integral curve of it starting at a given point. And as we will see, this boils down to solving a system of ordinary differential equation with given initial datum. So let us assume that we have a smooth vector field on the manifold, and let us assume that we want to find an integral curve of x starting at a given point. So we have our manifold here, we have the point on the manifold, and we want to look for, we have a vector field, so we know that at each point we will have the vector field that makes something, and we want to look for a curve passing through P whose tangent vector at each point is precisely the vector field we are considering, evaluated at that point. So which is the idea here? So now C of t is an unknown, so we want to find it if it exists. And how do we proceed? We start considering a chart about the point P. So this means that we consider some open set containing P and a chart possibly centered at P so that it maps P to the zero element of the space Rn where this map has its codomain. So in such a case, you saw last time that on this open set, you can use local coordinates to write your vector field locally with an expression like this one, where these AI, which are the components, are some smooth functions defined on the open set and whose values are in the real line. So in such a case, if we are on this open set and we are considering a generic curve C of t, which is our unknown curve, so for the moment, let's say C will go from some real interval to the manifold M, and it is unknown. And we first require that the vector field evaluated at C of t will be equal to the derivative of this curve. So the vector field evaluated at C of t is nothing other than taking these functions AI and evaluating them at Ct. So recall that these AIs will be our functions defined on U. So you will go from some, let's say, some interval here with C, you will go here, obtain some curve, and then with this, applying these AIs that are functions defined here, you will get some real number. So this AI of Ct will be functions defined on some open interval of the real line and taking their values in the real line. Moreover, again, you saw last time that if you have some curve on the manifold, then its derivative can be written with respect to the local frame induced by local coordinates in such a way. So it is none other than the time derivatives of the components of the curve C, of course, taking the linear combination with the vector fields, the local vector fields induced by these coordinates here. So this is what you already saw last time, and what we are requiring here is that this unknown curve satisfies the condition C prime of t, so its derivative equals x of ct. So we are comparing these two, we are requiring that they are equal, and as you can see from the second members of these identities, this is equivalent to say that the time derivative of the component ci of t equals the function ai of ct. So we'll get such type of equation for every I going from 1 to the dimension of the manifold. And what is this? This is, if you consider all of these equations, this is just a system of ordinary differential equations. But be careful, this is not a system of ordinary differential equations on the manifold. It is a system of ordinary differential equations on the image of this open set inside Rn. So we have a system of ODEs, and we know how to deal with it because analysis tells us how to deal with it. And so requiring that an unknown curve is the integral curve of some vector field boils down to obtain a system of ordinary differential equations involving the components of the curve with respect to a chart. And if we consider, together with the system, the initial condition, which is requiring that at time equal to 0, our curve passes through the point P, well, this will give you the initial conditions for all these unknown functions C1, T, C2, T, until Cnt. So in particular, the initial condition will be given precisely by requiring that at time 0, each component of the curve is precisely the coordinate of the point P we are considering inside the open set in Rn. So we have a system of ODEs, we have an initial condition, and so we can, everything is smooth, so we do not have any problem of regularity of any kind. And so we can use a theorem of analysis to conclude that any such system of ODEs with an initial condition has a unique solution. And in fact, the system we use is this, the result we use is this one, and which is a result of analysis. And this tells you that if we have an open subset of some space Rn, you choose a point in this open subset, and the function defined on this open subset, with values in Rn, which is smooth. Then, if you consider the differential equation written in this term with y an unknown function, then this has a unique smooth solution, which is defined on some open interval of the real line, and whose values are inside the open subset B. And once you have a solution which a priori is defined on some small interval containing the initial time you are considering, you can extend it until a maximal interval. And so at the end of the day, you will get some maximal solution, meaning that it cannot be extended further. Its interval definition cannot be extended further. And what does the uniqueness means? Well, it means that if you have another curve solving the same ODE with respect to the same initial point, then this solution has to coincide with the other solution you have on their common interval of definition. So this is what uniqueness means. And so as you can see, we started with a problem at the manifold level, and we reduced it to a problem of solving a system of ODEs with an initial data on some open subset of Rn. And once we have solved this with the aid of this general result, we can bring back the solution. So now we have a solution which is defined on some open subset of Rn, and we will bring it back to the manifold using the chart, so using the map phi. So in this way, we have, let's say, here our map phi has taken us in some open subset here inside some Rn. Here we have solved our ODE, so we obtained the solution, and once we have obtained the solution, we bring it back. We fit to the -1 to the manifold. So as you can see, we have used a result of analysis to solve this problem that had, if you want, a more geometric flavor, at least from the beginning. So this is precisely what we did here. Of course, if you remember from the courses of analysis, when you study ODEs, when you study system of ODEs, you can also investigate the dependence of the solution on the initial datum. So not only the, say, smooth dependence on the parameter, but also on the initial datum you are considering. And again, since everything here is smooth, we do not have any problem at all. So also in this case, the solution will depend smoothly also on the initial point we choose on the manifold. And this is precisely what this is telling us here. So if you want to consider the dependence of the solution on the initial datum, then you will think of the function y that we considered before as a function depending on two arguments, both the parameter t, which is, if you want, the time, and q, which is the point where your curve starts. So in such a case, you rewrite your flow equation in this way. So you will have the ODE, which now, if you want, becomes a kind of PDE, because you're taking the partial derivative with respect to the first coordinate only, and you require this equation to be solved, and you require the initial condition to be this one. And what's going on is that you have also a smooth dependence on the initial datum for your solution. And this is precisely what this theorem is telling you. In particular, if you consider your initial value problem in this form, so you consider function f, again defined as some open subset of Rn, then what is going on is that for every point you take on the open subset, you will get some open neighborhood of that point inside V, and some real number, some positive real number epsilon, and a function which now depends both on the time and on the point, which is smooth, which take values inside the open set V, and which solves this problem. So again, what does this tell us at the manifold level? Well, at the manifold level, this is telling us that we also have a smooth dependence of the integral curve of a vector field on the initial point where it starts. So in particular, if you take any smooth vector field on the manifold, choose a chart around a point P, then you will end up with a neighborhood of that point inside U and some positive real number, and a smooth map, which is this capital F here, for which the function f of tq is an integral curve of x starting at q. So in this case, what we have is that this function f t of q, if you consider q to be fixed, is none other than the solution, the integral curve of the vector field starting from the point q at t equal to 0. And in particular, if you put t equal to 0, you will get that this function, which will now be a function from w to u, is none other than the identity. So as you can see, we are obtaining also in this general case something that we obtained before in the first example on R2. The only difference is that now we are only working on some open subset and some open intervals of the real line, so nothing is defined in general on the whole real line and on the whole manifold. So we have such a smooth function we can define when we solve this problem of finding integral curves, and in particular, if you take any two real numbers s and t in the interval where this flow is defined, then if they are such that both the composition of ft and fs is defined and the function f at t plus s is defined, then as you can easily see, both these functions here satisfy our integral curves of x starting at the same point fs of q at time equal to 0. So if you put time equal to 0 here, you will get f of sq, so it will start from here. If you put time equal to 0 here, you will get f of 0 something, and we say just before that it is the identity. And so at time equals 0, also this one is fs of q. And they solve the same ODE. So if you derive with respect to the time, you will get the same ODE as before. And so this tells you by the uniqueness of the solution that these two have to coincide on their common domain. So whenever they are both defined, they have to coincide. And this tells you that in general, we have such an identity whenever both sides of this identity are defined. And as you can see, we obtained a generalization of what we saw before. So a map f behaving in this way, so a map like this one, satisfying this first property and the second property, is what is called a local flow generated by the vector field x. And in particular, what is going on is that for each q you fix, for each point you fix on the open set, you will get a function depending on the time t with values on the manifold, which is the so-called flow line, which is none other than the integral curve of the vector field x we are considering starting at the point q. And if it happens that this local flow is defined on the whole for every real time and on the whole manifold, then you call it a global flow. And this is precisely what happened earlier in the first example we discussed. So in the first example we discussed, our flow was defined on the whole R and on the whole R2. But in general, this is not always possible, as we saw in the second example, and you can only do such kind of discussion at least locally, let's say. So at least for some short times and in some small intervals, some small open sets of the manifold. And finally, yeah, we want to, I don't think we will use this, but let's just say this as a further information. A vector field whose flow is global, so whose flow is defined for every time and on the whole manifold, is what is called a complete vector field. So as you can see, in particular, when you have a complete vector field, and so when you have a global flow, then you will end up again with the so-called one-parameter group of diffeomorphisms. So your map, your global flow F, can be thought as a homomorphism, a group homomorphism between R and the diffeomorphism group of the manifold. And you just consider the time t and send it to the diffeomorphism of the manifold given by f of t. And so which will be the image of a point here. It will be just the integral curve of the vector field starting at the point you are considering at the time t. So this is what a global flow is, and clearly you can weaken this definition and talk about local flows. So a local flow will be something like this definition here, but defined only on some small time interval containing 0 and some small open set of your manifold. And what you require is that at the time equal to 0, this function here will be, let's say, locally the identity. So it will send the point to itself for every point in your open subset. And you require that it will be a group homomorphism whenever both sides of this identity are defined. So this is what you can say starting from the problem of vector fields and integral curves of vector fields. And so in particular, as an example, here we have again the example we met before. So the example of the vector field on R2. This is a complete vector field. The integral curves were circles. They are defined for every real time. And in fact, the flow equation in this case is just the equation sending each real time and each point in R2 to the rotation of the point with respect of an angle t in this case. And in particular, as you can see here, again, if you will derive f with respect to the time t and evaluate it at t equals 0, so that we are at the point, so let's recall here that at time 0, f0 of xy is just the identity, so it will be xy. And so the vector field x at the point xy will be the derivative of this capital F with respect to the time and evaluated at t equals 0. Derive this with respect to the time and you will get this matrix here, evaluate at t equals 0, and as you can see, you will end up precisely with the vector field we consider at the beginning of everything, so in the first example. So this is an example, so this is the first example we consider in the light of this discussion on local flows. Actually, here we have a global flow and this vector field in this example is complete. Okay, so this is the first part of this of today's discussion. And now we can move on and start discussing the so-called D bracket. So for this discussion, I have to recall this property that you discussed last time. And let me recall that we have this one-to-one correspondence between smooth vector fields on a manifold thought as smooth sections of the tangent bundle and the so-called derivations of the space of real valued smooth functions defined on the manifold. You saw last time that there exists such type of one-to-one correspondence, and we will use this interchangeably during this part of the lecture of today. So let's start considering. So now we want to define an operation. So our goal now is to define an operation between vector fields, which we shall denote by this bracket here. And this will be an operation taking two vector fields and giving you as a result another vector field. And we want to, first of all, understand which is a reasonable way to define such type of operation on the manifold. So let's start considering two smooth vector fields on the manifold, restrict them to some open subset U of the manifold, and we can, as I recalled before, we can think of them as derivations on the space of smooth functions, of smooth real-valued function defined on U. So choose any such a function f, and as you remember, since both x and y are smooth vector fields, you can consider y applied to f, and you will get a function which is again smooth, which is at each point is the derivative of f in the direction of y evaluated at that point. This is a function, and of course, once you have this, you can consider x applied to this function. So you can consider this one here, and here is just a notation to denote the composition of this function. So the function defined in this way. So you first consider f, apply y, and get another smooth function. This is a smooth function. Apply x, and you obtain a further smooth function defined on U. Also, I remember that I recall that both x and y are linear maps from this space of functions, and this map xy we have defined in this way maps C infinity of U into C infinity of U, and this again are linear. However, this does not satisfy the derivation property that you discussed last time. In particular, if you take any pair of smooth functions defined on the open set U, and you apply this new derivation, this new map xy, well, first of all, you will have to apply y, and since y is a derivation, you will get first the derivative of f with respect to y, and then multiplied by g, and then f multiplied the function obtained by taking the derivative of g with respect to y. Then apply x to this function here, and again you use the Leibniz rule also in this case, and as you can see, you would get first the derivative of this function here, which is this one. Then you will get this function times the derivative of g taken with respect to x, so this one here, and the same for the second summand. So as you can see, you will get, you don't get what you expect from a derivation, because you expect this summand here, you expect this summand here, but you do not expect neither this nor this one. So this tells you that even if this map xy is an R-linear map between smooth functions, well, it is not a derivation, so it does not correspond to a vector field on the manifold. What you have to do if you want to obtain a vector field on the manifold is to try to cancel in some way these two summands. Well, but now if you have a look at this expression, you see that if you compute the same expression but changing the roles of y and x, you will end up here with again these two objects and y and x switched in these two expressions. So this suggests that if you consider xy applied to the product and you subtract yx applied to the product, then you will end up without these two and only with the difference of xy and yx applied to f and then multiplied by g, and the same thing here, so f multiplied by the difference of xy and yx applied to g. So this is telling you that if you consider xy and you subtract yx, then this will be a map going from C infinity of U to C infinity of U. This will be R linear, and this will be a derivation. So this will send to zero, so this will make disappear the bad terms you have here. So this is a derivation, and so this will correspond to a vector field on the manifold. And so this suggests the way you can define a new vector field starting from two vector fields. is precisely this one here. So starting from to smooth vector field x and y on an open set, take a point P on the open set, you define what is called the Lie bracket and denoted in this way at the point P to be just the derivation defined in this way. So this is a derivation. At the point P, it would be just this expression here. So you take the derivative of any function f with respect to f, and then you apply y of p as a derivation on the function you obtain. And you do the same also for the first summand. And using the same calculation we did here with this new operation, you can show that this xy of p, defined in this way, is a derivation on functions, on germs of function defined around P. And thus, for what you saw last time, this is a tangent vector at the manifold. And in particular, since P is an arbitrary point belonging to the open set, if you make it vary, then you will end up with a vector field defined on U. And in particular, this is not just, so for the moment we started with x and y vector fields on U, and we obtained this bracket, which is, let's say, a vector field on U, but we do not know if it is smooth. And the answer is yes, and is given by this result here. So if you start with two smooth vector fields on the manifold, then the bracket of these two vector fields is also smooth. And so this bracket is actually an operation taking two vector fields, two smooth vector fields, and giving as a result another smooth vector field. How to show this? Well, if you remember, last time you saw that a section of the tangent bundle is a smooth vector field if and only if, when applied to any smooth function, gives you a smooth function. And this is exactly what you apply here to obtain the result. So consider any smooth function on the manifold. We have to show that this new vector field given by the bracket of xy applied to this function is smooth. But by definition, this is just xy minus yx applied to f. And it is smooth because by hypothesis both x and y are smooth. So this tells us that our map given by the bracket maps smooth vector fields to smooth vector fields. And so this is a way of obtaining a new vector field starting from two old ones. Of course, the properties of this bracket map are not exhausted by the fact that it is smooth and maps smooth vector fields to smooth vector fields. Clearly, as you can see from the definition, it is skew symmetric. So in particular, if you change the position of the vector fields you are considering, you will end up with minus the bracket of the vector fields in the initial position. So you have this skew symmetry property, and moreover, you have this so-called Jacobi identity that tells you that if you consider the cyclic sum of the brackets of three vector fields taken in this way, then you will end up with the zero vector field. And if you want to try to do this, is just an exercise. The cyclic sum means that you're just starting with x, y, and z in this order, and then you replace every, you exchange every vector field here in a cyclic way. So y goes here, z goes here, and x goes in the last entry, and you do the same here. So z goes in the first entry, x in the second, and y in the third, and you get this one, and then the sum is finished. If you do again a permutation, you will go back here. And again, also this one is just a matter of computation. So if you want to prove this, and this is an exercise I suggest you to try to do, just take any smooth function f on the manifold, consider this, apply this to f, and then use the definition of the brackets to see what you obtain. At the end of the day, after you did all your computations, you will end up with all summands that cancel pairwise, and then you will end up with 0. Well, now we have this property, so this new operation on vector fields. It is Q-symmetric. It satisfies this operation here, this Jacobi identity, and moreover, of course, it is also linear in the two components separately. These are the properties you require on such type of map to obtain what is called a Lie bracket and to obtain what is called the structure of a Lie algebra over some vector space. In particular, what we define here for vector fields is an instance of this more general algebraic object, which is called a Lie algebra over a field K. In particular, a Lie algebra will be a vector space over some field K you consider, together with a product denoted in this way, which is the bracket, which satisfy the following properties for every numbers in the field and every vectors in the vector space. So you want it to be bilinear, so it will be linear in each component separately, and so this will be just linearity. You want this anti-commutativity or skew-symmetry, so you want that if you exchange the roles on y and x, you will get minus the bracket, and you want the Jacobi identity to be satisfied. So whenever you have a vector space endowed with a bracket operation which sends two vectors in a third vector and satisfies these three axioms, then this is the structure you call a Lie algebra. And in particular, what we said before is that the set of all vector fields on the manifold together with this bracket operation is a Lie algebra. And so first example of the algebra over, in particular in our case, over the real numbers, is the set of all vector fields, smooth vector fields on the manifold with the bracket we just defined. Of course, you can define some simpler examples. For instance, on any vector space, you can define the bracket to be equal to 0 for every pair of vectors you obtain, you have, and in this way you get what is called an abelian Lie algebra. But in general, of course, you can have different types of Lie algebras, and we shall see other examples later. Yeah, just a remark, what is going on is that the bracket of a Lie algebra does not need to be associative. So in this sense, a Lie algebra is not an algebra according to the definition you gave last time. So if you remember, Maurizio at some point said that when you have a vector space, it may sometime happen that you can define also a product between vectors. And if this product satisfies some nice properties, then you get what is called an algebra. In such a case, we have this kind of product given by the bracket, but this is not associative. And so in particular, this won't define an algebra in the sense we defined, you saw last time. And so the example we discussed before is just the example of the space of smooth vector fields on the manifold with the bracket we defined before. And of course, we have other examples. So for instance, if you consider a vector space of squared matrices of order n over some field k, then you can define the bracket just as the commutator defined in this way. So just take the product of two matrices, x and y, in this order, and subtract the product of the matrices y and x. This gives the space of squared matrices the structure of a Lie algebra. So this is another instance of a Lie algebra. And more generally, if you have any algebra over a field, so if you have any vector space together with a product between the vectors, in the sense you discussed last time, then there is a way of defining a Lie algebra structure over this algebra, just defining the bracket as the product of the two vectors minus the product of the two vectors with the opposite order. And so, for instance, the case of matrices is just an instance of this more general case. But of course, if you don't remember what an algebra is, or you don't want to proceed in two algebraic work, then you can also ignore this last part. And I think that we can skip this information here. So you have some definitions of maps between Lie algebras, but we won't use them later. So I will skip this definition here. It's just a definition and does not add much more to what I'm going to say later. Okay, so this concludes the part about the algebras. So the first, let's say the first part on the algebras we are discussing today. And now we come with we have arrived to the last part of this chapter, which deals with the push forward of vector fields. So as I said before, if you remember from last time, if you start with a smooth map between smooth manifolds, then you can consider its differential at a given point of the manifold, and you will get a vector space, a linear map between vector spaces, sending a tangent vector at the point P to the first manifold to a tangent vector at the point FP to the second manifold. And if you have some vector x in the first tangent space, then you apply the differential and you get what is called the push forward of the vector x at the point P. So you will get some vector here in this other tangent space. So now the natural question is to ask whether you can do something similar also for vector fields. And the answer is no. The answer is no because this depends heavily on how the map is defined. And here is an example that illustrates this. So in general, what you know is that X is a vector field on the manifold you have in the domain. And if it happens that, for instance, two different points of your manifold N are mapped to the same point of M by F, well, there is no reason why the image of X at the two distinct points has to be the same once you do the push forward, so once you do the differential. And in fact, here you have an example with the projection. So in this case, you have R2, and you have this map here, which is just the projection onto the first component. So it will send a pair x, y, it will be projected just to x. And so as you can see here, you have various points on the y-axis that are all mapped to this point here. And you have various vector fields. So you have various vectors belonging to the same vector field. And of course, there is no reason why all of them have to be mapped by this map in the same vector field here, in the same tangent vector here. So in general, you do not have an easy way to define the image of a smooth vector field using a smooth map. Actually, there is one case where this is well defined, and this is the case when the map you are considering is a diffeomorphism of manifolds. So in such a case, I recall that. So it is a smooth map, which is an inverse, which is also smooth. So in this case, the map is in particular injective. And so we won't have this ambiguity we have here. So we do not have the risk that different points are mapped in the same point. Any point in N is mapped to a unique point in N, and so it is the image of xp through the differential of f at p is well defined. So this makes sense, is well defined. And moreover, f is surjective. And so this ensures you that the map you define in this way, so this f star x defined at the point fp in this way, is defined on the whole of M, because f is surjective. So if f is a diffeomorphism, you have this map f star, which is well defined. It will map points of M to objects in Tm, and so this would be in particular a section of the tangent bundle. And moreover, it is smooth, and so it is a genuine smooth vector field on the manifold. And an easy way to see why it is smooth is just using composition of smooth maps. So you start from M, apply the inverse of F, which is a smooth map. You will end up in N. Then you have X, which is a smooth vector field. And then you have the induced smooth map that the diffeomorphism F induces at the level of tangent bundle. So this is a smooth bundle map. And this vector field defined as the push forward of X is then well defined and smooth, as it can be seen as the composition of smooth maps. So in the case when you have a diffeomorphism, it makes sense to define the push forward of a vector field. But in the general case, there are some issues that do not allow you to do this. And so in particular, this lets you considering this notion of related vector fields. So again, we consider a smooth map between smooth manifolds, and we can introduce the notion of the so-called related vector fields. So what are two related vector fields with respect to a smooth map for us? So starting with a smooth map, consider a vector field X on the domain, so on N, and we will call X a vector field which is F related to a vector field over line X on the manifold M, if for every point of M, the differential, the image of X of P with respect to the differential of X at that point is precisely the value of the vector field over line X at the point F of P. So recall that the differential or the push forward of the map F at the point P is a linear map between these two tangent spaces. So what we are requiring, so in this definition, is that for each point of the domain, so for each point of the manifold, the map is defined on, this identity have to hold. So if this happens for each point, we say that the two vector fields are F related. And so in particular, what we can say is that if F is a diffeomorphism, then the push forward is defined, we said this a few minutes ago, is a smooth vector field, and by its very definition, the vector field X is F related to the vector field F star of X. We will see later that there are also examples of vector fields that are related by a map which is not a diffeomorphism. and this will be the case of Lie groups. And of course, the map will have to satisfy some particular properties in order for this to be possible. Okay, so now we have a condition that allows us relating the F-related vector fields, and in particular, if you have a smooth map between manifolds, then you have that a vector field X on the first manifold and the vector field over line X on the second manifold are F-related if and only if for every smooth function you take on the codomain, this following identity holds. So let's make some comment on this. Here we have the composition of this function here in F. So this will be a smooth function defined on N with values in R. And so it makes sense to consider X applied to this function. Here we have this function G, which is a smooth function on M. It makes sense to apply the vector field over line X to it. This will be a smooth function on M, and then it makes sense to apply it to capital F. So this is a test to prove that two vector fields are related by means of some smooth function. And here you have a proof, which is just an application of the various definitions. So if you assume that X and over X are F-related, then by definition, they have to satisfy this identity here for every smooth function G on M. So by definition, we know that for each point, the differential of F at P applied at X of P has to be equal to the vector field over line X at the point F of P. This means this is the definition of F-related. Then these are vectors at the point here, F of P. Apply them to the function G in this way. Then you recall the definition of the differential. You saw this last time. This is just the vector xp applied to the composition of G with the function f. And here you apply the definition of the of this function here, which is just what you obtain taking the derivative of G with respect to x and then applying it at the point f of p. And as you can see here, again, for the same reasoning you used to go from here to here, also here you will have x applied to the composition of f and g at the point p. This is valid for every point, and so this tells you that this function here has to be equal to this function here. And so it is precisely what the proposition claims. And the converse is obtained by reversing this argument. So start from here and proceed in the opposite way. Why is it useful? Because it can be used, for instance, to show that the Lie bracket is in some sense natural with respect to this condition of being F-related for vector fields. In particular, what happens is that if you have a smooth map between smooth manifolds, and if you assume that you have a smooth vector field X and a smooth vector field Y on N that are F-related to the smooth vector field over line X and over line Y on N, then the Lie bracket of the two vector fields on N will be F-related to the Lie bracket of the two vector fields on the manifold N. And you can show this just applying this proposition here we have just discussed. So you have to show precisely this, that for any smooth function on the manifold, if you consider the Lie bracket of the vector field x and y and you applied it to G composed with f, you will end up with the Lie bracket of overline x and overline y applied to G and then composed to f. This is precisely what we are considering here, but for the Lie brackets now. And to show this, just apply the definition of the Lie bracket and then use this proposition here for y and for f, for y first and for x then, you will end up with this, and this is nothing other than the bracket of over 9x and over 9y applied to G and then composed to F. So using this proposition in particular, so using this result here in particular, you can show that the bracket operation we defined earlier behaves well with respect to vector fields which are related by means of some smooth function between manifolds. And this will be useful later, again, for the discussion we are going to do on the groups. I added such a result that I think is a nice result. It does not appear in the book by 2. And it is a kind of naturality also of integral curves. So another nice result, this is taken from the book by Lee. And this tells you that having F-related vector fields means that there is a relationship between their integral curves that we discussed earlier. In particular, if you have two smooth manifolds and a smooth map between them, and you have a vector field x on M and a vector field y on N, which are F-related, then they are F-related if and only if this map F takes integral curves of x to integral curves of y. And this means that if you have an integral curve of x as defined earlier, then the composition of y of this integral curve with F will give you an integral curve of y. And the situation is precisely this one. So here you have the manifold M, you have the vector field x with its integral curve, you have the map capital F from the two manifolds, and what this result is telling you is that if the vector fields are related by means of this function F, then the integral curve of the first are taken into integral curves of the second by the map F. So this is another way of thinking about related vector fields on a manifold by means of smooth maps. And I will then give you also this presentation so that you can also examine more in depth the proof of this result, but it is just a computation using the definition. So you can easily see it also on your own. And as an example, for instance, you can see this very clearly in the first example we considered. So again, if you consider the vector field on R2, the first one we consider, which is this one, well, we saw that this function f here gives the integral curve starting at the point 1, 0, at time 0. And what it is going on is that the vector field on R given by d of dt, so the global vector field you have on R, is f related to the vector field y on R2 that we were considering. And it is related by means of this function, which, if you remember, was the integral function, the integral curve of the vector field y on R2. And in fact, if you take the differential of x at any time t0 in R, and you evaluate it at the tangent vector d of dt at t0, then remember from last time what we said, the differential, you can compute it just considering a curve passing through the point t0 at time 0 with derivative with tangent vector, this vector here, and then consider this curve, apply the function f, and then take the derivative at time 0. Of course, here we are in R, and so we have a natural curve to consider, which is just t plus t0. This is a curve starting at t0 at time 0, whose tangent vector at time 0 is precisely this vector here. But what is this f composed to this curve here? This is just cosine of t plus t0 and sine of t plus t0. Take the derivative with respect to the time and evaluate it at t equals 0, and you will end up with minus sine of t0 cosine of t0. Who is this? This is just y evaluated at the point f of t0. And so, as you can see from also this example, what we showed is that this vector field on the real line is related to this vector field on R2 by means of this map, or by this means of this move map F, and this move map F maps precisely the flow of the vector field d of dt starting at t0, which is this curve, to this other curve, which is precisely the flow of y starting at the point cosine of t0, sine of t0. This is precisely the example we discussed earlier, coming from page 152. So this is an additional result that gives you another property of f-related vector fields. Then here you have some problems. I just highlighted some. Let me mention briefly what they are, and then most of them you can try to solve them as an exercise. So the first problem, which is actually a computation using what you saw last time, tells you that if you have an odd-dimensional sphere, then it always has an over-vanishing smooth vector field. And in this case, you are defining the odd-dimensional unit sphere S of dimension 2n minus 1 in R2n as in this way, so by means of this equation. And then this problem tells you just to compute, to show that this vector field X, defined in this way, is a tangent vector field to the sphere. It is clearly nowhere vanishing because of its definition. Here you have these coordinates that are never 0 on the sphere. And to show that it is a tangent vector to the sphere, it is sufficient to show that it is orthogonal to every point of the sphere by means of the usual Euclidean product you have on R2n. So it is similar to some exercise you discussed last time. So the crucial fact here is that once you have an odd-dimensional sphere, then there exists a smooth vector field which is nowhere vanishing. This happens only in the case of odd-dimensional spheres. What it can be shown using results of algebraic topology is that if you consider an even-dimensional sphere, so think for instance at the simplest example, so the two sphere you discussed and considered last time, then in that case, on every even-dimensional sphere, every continuous vector field must vanish at some point. This example here tells you that this does not happen in the case of odd-dimensional spheres. There exists at least one smooth vector field, which does not vanish anywhere. Then there are some examples of computing maximal integral curves, and you can try to do these examples on your own. This is just a matter of writing down the ODE and the Cauchy problem you have to consider, and then understand which is the maximal time of existence of the solution. And here there are some examples, and I already wrote some solutions in every case. So as you can see, these are very similar to other examples, to the other example we considered before. So for instance, here you will end up with this ODE problem. So x dot will be equal to x, y dot will be equal to minus y, and you will integrate it starting from each point you want, and you will get the solution. And then, yeah, there are some exercises that you could try to do to to try to become more confident with these techniques if you want. And there are also some nice exercises also involving the brackets of some simple vector fields, both of theoretical nature, such as this one, and both of practical nature. So compute the bracket of two smooth vector fields on R2. Okay, so the last comment I wanted to do on this section involves this the bracket under a diffeomorphism. In particular, so as I said before, if you have a diffeomorphism between two smooth manifolds, then starting from two smooth vector fields on the domain, so on N, then what happens is that if you take the bracket and then you consider the vector field defined by the push forward by means of X, and this is well defined because F is a diffeomorphism, then you will get the bracket of the push forwards of the two vector fields. And this is just a consequence of one of the last results we discussed. In particular, since F is a diffeomorphism, we know that X is a vector field of N, which is F related to the F star X. This is the example 14.15 we discussed earlier. And Y is a vector field on N, which is F related to F star Y. These two are vector fields on the manifold M, and by the proposition 14.17 we saw before, we know that the bracket of X and Y is F related to the bracket of F star X and F star Y. But this means precisely what it is written here. So this means precisely that if you consider this push forward of the bracket of two vector fields by means of a diffeomorphism, then you will end up with the bracket of the push forwards. Okay, oops. So this concludes this first part, and we can move. Let's say, so it's 4:15, so maybe I can just say something as an introduction, and then we can make some break before moving on. So let's start with this new topic, which involves the groups and the algebras. And you already met the groups in the previous lecture. So as you define them, you saw that they are a merge of two different structures. We have an algebraic structure, which has the structure of a group, whose definition I recalled before. And you have a structure of a smooth manifold. So you have these two different structures involved in the same construction. So this is precisely what a group is. It is a manifold, and it is also a group for which the group operations are smooth when seen as maps between smooth manifolds. What one can say that a group is a homogeneous space, so locally it looks like the same around any point, and I shall say something about this later. And in particular, to study the structure of a group is enough to examine what it is going on in the neighborhood of the identity. And moreover, real groups are related to the notion of the algebras we introduced before, and this is because every group turns out to have a canonical bracket operation that makes it into a Lie algebra. And in particular, what one can show and what we will see is that the tangent space to the Lie group at the identity with this bracket is what is called the Lie algebra of a Lie group. And as the name suggests, the first person who studied such groups was Sophus Lie here. And its aim at the beginning was to study the group of transformation of a space as a continuous analog of the group of permutations of a finite set. So at some point there was a well-developed theory about a group of permutation of finite sets, and then the idea was to try to study a group of continuous transformations of a space following in some sense the same philosophy. And yeah, in fact, we will see in particular that Lie groups arise as, in some sense, transformation groups of a smooth manifold. Okay, so let's start with some definitions before the break. And so the approach that this book uses is to discuss various examples of matrix groups that turn out to be Lie group. Last time, if I remember well, you saw already some examples of Lie groups, and we will meet some of them again today. So let's start recalling what is a Lie group. And so a Lie group, as I said before, is given by combining two different structures we already met. It is given by combining an algebraic structure given by the structure of a group and a differential geometric structure given by the structure of a smooth manifold. So in particular, a Lie group is a smooth manifold, and we shall denote this by such a type of letters, in this case, this capital G, which is also a group such that the group operations that are the multiplication, which is denoted by this mu, and the inverse, which is denoted by this I, are both smooth maps. So we have these operations and we want them to be smooth if we think of them as maps between smooth manifolds. Once you have a Lie group, you can consider some well-defined maps on the Lie group. Two special maps you can consider are the so-called left multiplication and right multiplication, which are just given by taking an element of the Lie group and considering the map, mapping the group to itself, which sends each element to the group just to the product on the left of this element by the element A we fixed before. This is the left multiplication, and similarly you can define the right multiplication in a similar way by multiplying any element of the group by this fixed element A on the right. So you have these maps that are smooth because they only involve this product mu that is smooth, and in particular they are diffeomorphisms of the manifold. They are smooth maps and they have a smooth inverse. The smooth inverse is none other than the map given by the left multiplication by the inverse of the group element. So we have these special diffeomorphisms of our manifold, of our Lie group, and of course we can consider also in this setting the notion of a homomorphism of group but between Lie groups. So I recalled before the definition of a homomorphism between Lie groups, between groups, sorry. So from the algebraic point of view, if we have Lie groups, then a homomorphism between two Lie groups will be just a smooth map between these two smooth manifolds, which is also a group homomorphism, so which preserves the group operation we have on the two groups separately, so which satisfies this identity that we already met earlier. So as you can see, both the algebraic aspects we discussed earlier and the smooth aspects we also discussed and you also met last time, we get these new notions. So in particular, as you can see, if you like more functions than these expressions involving algebraic objects, if you want, you can rewrite this identity here as the composition of two maps. In fact, this is just the composition of the smooth map F with the left multiplication by H, and this is the composition of F with the left multiplication by FH. And in particular, as I said before, if you have a group homomorphism, this maps the identity of the first group to the identity of the second group. This follows immediately from the definition of group homomorphism. And so in particular, every homomorphism of Lie groups will send the identity element of the first group to the identity element of the second group. As you can see here, from now on, it is customary to denote the identity element of a Lie group by the letter E instead of the symbol 1, as I did before. And in particular, once you have a Lie group homomorphism, you can also define what is a Lie group isomorphism. So you can define an equivalence between Lie groups. And I added this definition that does not appear in the book by 2. And in particular, if you have a Lie group homomorphism, so this smooth map preserving the group structure, which is also a diffeomorphism, then this is what is called a Lie group isomorphism. The fact that it is a diffeomorphism means that it is a smooth inverse, and using the fact that it is also a group homomorphism allows you to show that also the inverse is a Lie group homomorphism. So also the inverse is not only a smooth map, but it is a homomorphism between the two groups. So whenever it happens to have a Lie group isomorphism, what you say is that the two Lie groups are isomorphic as Lie groups. And this means that they are, in this sense, they are equivalent. And we shall say some examples of isomorphic Lie groups later. Here are some examples of Lie group homomorphisms. Last time you discussed the circle as an example of a Lie group. If you think of it as the circle inside the complex numbers, so you consider the representation using the complex exponential, or if you prefer, you think of it as the complex number given by cosine of theta plus I sine of theta for each theta in R. And this map here, sending each theta in S1 to itself in C star, is a Lie group homomorphism. The exponential map sending a real number to the exponential of the real number is a Lie group homomorphism between the real numbers with the sum, considered as a Lie group with the sum, to the real numbers without the zero, considered as a Lie group with the product. And moreover, you have other Lie group homomorphisms, for instance, this one between the real line and S1, sending each real number to the point in S1 given by e to the 2 pi I of t. And so if you prefer, think of this in terms of sine and cosines of the angle, and think of this as a complex number, and so use the representation using the Gauss plane to represent it on a two-dimensional plane. You can extend this homomorphism when you consider Rn as a Lie group with respect to the sum, and you consider the n-dimensional torus that I think you already met last time, which is just the product of the circle by itself for n times. And you can define this Lie group homomorphism just by sending the n-tuple of T1, Tn to every single element defined in this way, which is a point in every of these circles. So you're kind of using this map for n times. Also, the determinant map is a Lie group homomorphism between the general linear group and the real numbers without the zero. So this is because of the formula by Binet that tells you that the determinant of the product of two matrices is the product of the determinants. And finally, there is also this operation that is useful when one deals with Lie groups, which is the so-called conjugation, which is a map, a smooth map between a Lie group and itself, which is just given by, oops, sorry, here I wrote the wrong definition. is defined in this way. So fix an element G in the Lie group, and then this conjugation sends every element H of the Lie group to this product here. This is the conjugation, and it is a smooth map and a Lie group homomorphism. So the fact that it is a Lie group homomorphism follows from the fact that here we are using just the group rules to define the map. It is smooth because it is the composition of smooth maps. And it also has a smooth inverse given by C of G to the minus 1. So it is actually a Lie group isomorphism. And finally, so to conclude before making a break, I wanted to recall this theorem saying that once we have a Lie group homomorphism according to the definition we gave before, then this map has constant rank. So this is an instance of maps having constant rank as you defined in the previous lecture. And the proof is actually really simple because it uses the definition of a Lie group homomorphism and shows that the differential of X at any point of the Lie group H has the same rank as the differential of X at the identity. And so in particular, since the point H0 is arbitrary, this shows that the rank is constant and equal to the rank of the map of the differential of F at the identity. And to show this, you just apply the definition of a Lie group homomorphism. So you know that if you apply F to the product of two elements of H, this is the product of the images because F is a Lie group homomorphism, and then you can interpret products on the left using the left product maps. So you will end up, since H is an arbitrary point, you will end up by observing that you have this identity of functions. So if you compose F with the left multiplication by H naught, then it is the same of composing capital F with the left multiplication by F of H naught. Now, just take the differential of this map at the identity of H and use the chain rule you introduced last time to split it as the composition of two differentials on each side. Here we have the differentials of the left multiplication maps that are isomorphisms, because the left multiplication maps are diffeomorphisms. So in particular, this tells you that the rank, they don't modify the rank, they are maximal rank maps. And so this tells you that both the differential of X of F at H0 and the differential of X of F at the identity of the Lie group H are have the same rank. And so this tells you that any Lie group homomorphism has constant rank. And last time you saw how important are maps with constant rank. They have some nice local properties, and also this condition here of having constant rank can be used to draw conclusions that allow one to conclude that a map which has constant rank and satisfies some further property is actually a submersion, an immersion, or even a diffeomorphism according to the definitions you gave last time. And in particular, this is a theorem again that you can find in the book by Lie, which is the so-called global rank theorem, that tells you that if you have a smooth map between smooth manifolds, which is a smooth map of constant rank according to the definition you gave last time, then if the map is surjective and it has constant rank, then it is a submersion. So its differential is surjective at each point. If it is injective, it is an immersion, and if it is bijective, it is a diffeomorphism. I haven't written the proof of this result because it involves heavily the topology, some topology results. So take this just as an information of why it is important to know that, for instance, if you have a Lie group homomorphism, then it is a map of constant rank. Because, for instance, as soon as you know that your Lie group homomorphism is injective, then you will know that your map is an immersion. As soon as you know that it is bijective, you will know that it is a diffeomorphism on Lie groups, and so on. Okay, I think that we can stop here for the first part and make some break, and then restart. John will tell me at what time we want to restart with the second part.
Alberto, maybe 10 to 5 if it's for
okay.
You. Okay, just
yeah.
Between 15 and 20 minutes.
Okay.
See you later. Thanks.
Yep. Okay, so maybe we can start again. And so we introduced what Lie groups are, and we saw some first properties of Lie groups and some properties of some natural maps that one can consider between Lie groups. Now in this book there are some examples. Probably you already met some of these examples and you already commented them last time. So the first example is the general linear group, which is a Lie group, and it is just a group of matrices whose determinant is different from 0. And as you saw last time, this is a Lie group because it is an open subset of the set of matrices. And this is a notion from topology, and you said something about this last time. So what does it mean that it is open? It is the complementary of some closed subset, for instance. And in particular, in this case, we can describe the general linear group as the complement in the space of matrices of the set of matrices whose determinant is 0. The determinant is a continuous map, and the general result in topology tells you that if you have a continuous map, then by definition the counter images of closed subsets are closed subsets in the topology of the codomain and the domain respectively. So this is a closed subset in the space of matrices, and the general linear group is the complementary of this closed subset, and so it is open. And being open, it is an open submanifold of this manifold here of n times n matrices. And so it has a natural smooth structure induced from the smooth structure of this space. Another example you saw last time is the special linear group, which is the subgroup of the general linear group made by the matrices whose determinant is 1. And you discussed this example, I think, telling you that the special linear group is a regular submanifold of the general linear group whose dimension is n squared minus 1. And here is how it works. So this should be what you saw last time. So you consider the determinant map, and you can think of the special linear group as the inverse image of 1 via this determinant map. And so you want to show that it is a regular submanifold, and what you do is to show that it is a regular value. This means that every matrix in the counter image, in the pre-image of 1 via this determinant map is such that the differential of the determinant map at that matrix is surjective. And in fact, what it is shown in example 913, I think, is that a matrix, n times n matrix, a square matrix, is a critical point of the determinant map if and only if all n-1 cross n-1 minors are 0. And this means in particular that the matrix has 0 determinant. And so this means in particular that 1 is a regular value for this map. And so in particular, the special linear group is a regular submanifold, or if you want, an embedded submanifold of the general linear group whose dimension is precisely whose codimension is precisely 1. It's precisely this dimension here. And so whose dimension is n squared, the dimension of the general linear group minus 1. So you discussed this first part last time. And moreover, what's going on is that the multiplication map is smooth. And this is because if you multiply two matrices in SLN R, you get another matrix with determinant 1. So it is again in SLN R. And since the special linear group is a regular submanifold of GLN, you can restrict the codomain of the usual multiplication map going from SLNR to SLNR into GLNR to get a smooth map with values here. And the same holds also for the inverse map. And you should have seen and discussed these results last time. So in particular here, the crucial fact is that the special linear group is a regular submanifold. This is what allows you to define both, to conclude both that the product map and that the inverse map are smooth maps from the special linear group to itself. So they are smooth, and so in particular, it satisfies all the properties, all the requirements in the definition of a group. And as this tells you, of course, you can apply this also for the special linear group when you consider complex matrices instead of real matrices. Another nice example that you probably have discussed last time involves the so-called orthogonal group. And by definition, you can define it as the set, as the subgroup of the general linear group whose matrices satisfy this identity here. So you take the transpose of the matrix, multiply it by the matrix, and you get the identity. So these are the, if you want, the transformations, the matrix representation of the linear transformations that preserve the natural Euclidean product that you can define on the vector space Rn. And so in particular, as this identity holds for every matrix in On by definition, you can say that On is the inverse image of the identity matrix under the map sending a matrix to the product of its transpose by itself. Last time you have shown using a certain argument that the map F defined in this way is a constant rank map. And then by the constant rank level set theorem, you conclude that the orthogonal group is a regular submanifold, so an embedded submanifold, the image of an embedding of GLNR. The bad part of the constant rank level set theorem is that you can apply it to conclude that some subset is a regular submanifold, but it does not give you any information on the rank of the manifold, so it does not give you any information on the codimension, on the dimension of the regular submanifold. In particular, last time you just showed that the rank of F is constant, but the argument you used did not allow you to indeed say which is the rank of this map. And so now we are going to do this in order to determine, so let's say, in order to prove again that the orthogonal group is a regular submanifold of the general linear group, and in order to determine also its dimension. Which is the idea? We will use the so-called regular level set theorem. And in this case, as you can see, we will determine the dimension of the orthogonal group. How to do this? Well, the key observation is that the product of the transpose of a matrix by itself is a symmetric matrix. This means that if you consider the transpose of this product, you get again this product because of the properties of the transpose of a square matrix. So in particular, what it is going on is that the image of this map F that we defined before, so from GLN R to GLN R, that maps A into the transpose of A times A, is actually inside the space of symmetric matrices inside the general inner group. So in particular, you can think of F as a function going from the general inner group to the space of symmetric matrices. And what's going on is that the space of symmetric matrices is a vector space, and in particular, it is a proper subspace of the space of squared matrices, and you can compute its dimension. Its dimension is this one, is n squared plus n over 2. And the idea is that once you have a symmetric matrix, then a basis is given by the matrices having zeros everywhere, but on each diagonal entry, and such matrices are n in total. And then you will have other matrices which only involve each element on the, let's say, on the upper triangular part of the matrix. And so in particular, so let's say there is not so much space, so you will have, for instance, 1 and all zeros, and you repeat this for every element in the diagonal, and you have n matrices of this form, and then you will have something like 0, 1, and every other thing is 0. This is another symmetric matrix. And how many matrices of this form do you have? You have the sum from n minus 1, which are how many elements you have here, to n, to 1, sorry, which are which is the amount of entries you have in the upper triangular part of the square matrix. So they are the sum of all numbers from 1 to n minus 1. So at the end of the day, a basis of this space, of this vector space Sn, is given by a number of elements, which is given by the sum of all natural numbers from 1 to n, and this sum is precisely n times n minus n plus 1 over 2. So we know the dimension of this space. We know that the general linear group has dimension as n squared. It is an open subset of the space of matrices. So well, now we want to compute the differential of this map. And to compute the differential of this map, we consider a matrix here, and the differential will go from the tangent space of to the general linear group at that matrix to the tangent space of the space of symmetric matrices at the point f of a. But S of n, the space of symmetric matrices, is a vector space, so it is naturally isomorphic to itself. So here you may think of the image of this differential as the vector space Sn itself. Here you have the tangent space at the GLN R. It is an open subset of the space of matrices. And so this tells you, as you saw last time, that if you consider the tangent space at some point, then it will coincide with the tangent space to this bigger space at that point. And in particular, again, since this is vector space, the tangent space of GLN R at the matrix A is canonically isomorphic to the space of n times n matrices. So the differential of x at some point, so at some invertible matrix, is a linear map going from R n times n to Sn. You may think of it as a method like this. And now we want to compute it. And how can we do? Well, we do as you discussed last time. So we have to choose a curve in GL and R starting at the point we want. So starting at the matrix A in GL and R, whose velocity at time 0 is any matrix X. Any such curve can be considered locally. It can be defined in a neighborhood of A. This is the content of this proposition that you discussed in the first lecture. And so in particular, to compute the differential of this map F at A evaluated in any tangent vector, so in any matrix in R n cross n, you just have to compute the time derivative of this function evaluated at the curve, and then evaluate the derivative at time equal to 0. But what is this function? This function is just the transpose of the matrix times the matrix. So it will be the transpose of C of t times C of t. You derive it, use the product rule. Here there will be a problem at the end of this section, but it is just a computation in coordinates if you want. So you have a product rule here. So you have the derivative of the first times the second, and the same, the first one times the derivative of the second. Evaluate at t equal to 0, and what you get is the derivative of C, which is x at time 0, which is x, and you get transpose, and then you have C at time 0, which is precisely A, and the same for this second sum. So you will end up with the differential of x at A evaluated in the vector x, so in the matrix X, which is given by this formula. So it is the transpose of x times A plus the transpose of A times x. So now we have to show that this map is surjective at every point A, so at every matrix A in the orthogonal group. This is the definition. This is what we have to check in order to show that the identity matrix is a regular value for the function f we are considering. So let's take any matrix, any orthogonal matrix. So let's recall that this is the f minus 1 of the identity matrix. So take any matrix here, take any symmetric matrix which is in the codomain of f, of the differential of f. Then what we ask is whether there exists a matrix X for which this object here, this matrix here, equals the matrix B we are considering. If this happens, then this map here, this differential, is surjective at each point A in the counter image of the identity matrix. And so I will be a regular value and ON will be a regular submanifold. And as an observation here, one can observe that since if you consider this first summand and you consider the transpose, you will get the second summand, and so it is enough to solve this equation here instead of this one, because a solution of this equation here will give you a solution of the original equation we were considering. And this is precisely because of the fact that B is a given symmetric matrix. But if you think a moment about this equation, X is an unknown matrix, the transpose of A is the transpose of an invertible matrix, since A is a matrix in the orthogonal group. So you can consider the inverse of this one, and you can solve this equation and obtain who is X. X is precisely 1/2 of the inverse of the transpose of A times B. So this shows that the differential of F at any matrix in the orthogonal group is surjective. And so this tells you that the orthogonal group is a regular level set of this map F. And so in particular, it is a regular submanifold of the general inner group. Which is its dimension? Well, the regular submanifold theorem tells you that the dimension is the dimension of the ambient space, so of GL and R, minus the dimension of the target space, which is the space of symmetric matrices. So the dimension of the orthogonal group is given by this difference here, and so it is just n squared minus n over 2. So this is, if you want, an application of a theorem that you discussed in the first lecture. And this tells you in particular, so we saw two examples, actually three examples of Lie groups that are all matrix groups: the general linear group, the special linear group, and the orthogonal group. And in two cases, we saw that we got some embedded submanifolds, which are the special linear group and the orthogonal group. And we proved that they are embedded. They are also subgroups from an algebraic point of view. And so, in fact, since we started thinking about Lie groups as algebraic objects with a smooth structure, we can say, okay, we have such type of geometric object. But of course, once you have a group in algebra, you can also consider what are called subgroups of the group, which are subsets that are groups on their own for the restriction of the product rule of the group to the subset. So since it makes sense to talk about subgroups in algebra, it will make sense to talk about Lie subgroups in this setting. And so it makes sense to introduce the notion of Lie subgroup. And pay attention to the fact that we require some conditions in this case. So what is given a Lie group, a Lie subgroup, will be, first of all, an abstract subgroup H of G. Abstract subgroup means exactly what I said before. So it means that it is a subset of G such that for each element you take in this subset, their product stays in the subset and the inverse of any element stays in the subset. So it is a group on its own for the restriction of the product that you have defined on the group, on the bigger group G, on the ambient group G, if you want. So this is the algebraic condition. Then we have a condition of H inside G as a submanifold. Remember that G is also a smooth manifold. We want H to be an immersed submanifold of the Lie group G. This means that H is the image of an injective immersion, as you discussed last time. And finally, as you saw, there are some issues related to the fact that a manifold is only immersed and not embedded. In particular, it is not for free that the restriction of the codomain of some smooth maps defined on the submanifold are again smooth. And in fact, you have to require that the group operations on H are smooth with respect to the smooth structure you have on H. So the fact that H is immersed means in particular that it does not, its image in G via this map does not have the topology induced by G. And so this is why you have to require that the group operations are also smooth. So this is what you need to define a Lie subgroup. And so in particular, as you can see, there is also this observation that I already told you. So of course, this tells you that since we have an immersion, if you consider the inclusion map, then you will get that the multiplication is a smooth map if you see it as a map going from H cross H into G. So you just compose the inclusion of H inside G with the multiplication of G. This is the composition of smooth maps, so it is smooth. But since H is immersed and not embedded, you are not allowed to conclude that this composition is also smooth as a map from H across H to H. And so this is why condition 3 is mandatory in the definition. And now there is a nice example that emphasizes this difference between what are immersed Lie groups as immersed submanifolds and the difference between them and the let's say some stronger condition which might be requiring that the Lie group you have is also an embedded submanifold, and so its image inherits the topology from the ambient space. And the example is this one given by the lines with irrational slope in the torus. So last time we discussed the torus, the two-dimensional torus, and among the possible ways of defining it, well, you can define it as the quotient space of R2 over Z2. What does this mean? Well, this means that you consider pairs of points in R2 and you define an equivalence relation between them. They will represent the same point of this quotient space if and only if their difference, which is just the difference of the coordinates, as defined usually, belongs to Z squared. So if this pair of points represent the same point in the torus, if and only if the difference of the x and the difference of the y's are integer numbers. If you don't like this presentation, you can also think about the identification of the two torus with the product of S1 cross S1 that we also mentioned before. And you can identify this with R2 over Z2 by means of the map sending the pair x1, x2 to these two objects, to these two complex numbers inside S1 cross S1. Using some theory of groups, you can show that this is a group homomorphism whose kernel is precisely Z2, and so you get an isomorphism between S1 cross S1 and this space here. So you have these two equivalent ways of thinking about the two torus. So now what we are doing is to consider a line through the origin in R2. And what's going on is that if you consider the projection from R2 inside the torus, then you get that the image of this line, which we will denote by H, later there will be an image and everything will be clearer, might be a closed curve if and only if the line in R2 goes through another point of Z2. So goes through a point given by a pair of integer numbers. And this happens if and only if, since the line passes through the origin, this happens if and only if the slope is a rational number or it is infinite. Otherwise, so in such a case, what you get is a closed curve diffeomorphic to a circle, and it will be a regular submanifold of the torus. The bad fact is when you have a line passing through the origin in R2 whose slope is irrational. In such a case, your image in the torus will not close up. So you will get what is called a dense subset of the torus. So you can restrict the projection to L and get a one-to-one immersion of this line inside the torus. And you can give the topology induced by the map. Now we will see what this means. So this is the situation. We are considering here R2, so this is the usual plane. We are considering all this grid given by integer values where y and x are integers. And so we are saying that we are considering as the same point all pair of points such that difference of the x and their y's is an integer number. So in particular, by means of this identification, these red dots you see here in the image represent the same point on the torus, since they differ by an integer. Every point inside this square is a unique point of the torus, while the points on these two vertical lines and the points on these two horizontal lines are identified one to each other. So this means in particular that if you focus only on this square, you will get the torus just by identifying these two sides and these two sides in the way described here. So you should have seen this last time. So you will you have this squared with the sides identified. So the green one identifies with the green one. So you glue them. You use the three-dimensional space to make this gluing, and so you will end up with a cylinder. And then you have to glue the cylinder along these blue circles. And when you glue it by deforming it a bit, you will end up with the torus. So in particular, as you can see, these lines, these blue segments where we started from are now a circle in the torus, and also these two green segments are a unique greater circle again in the torus. So this is the algebraic description. This is, if you want, the manifold description. And in particular, as you can see, all these red points will close up in a unique point of the torus. So as you can see here, we have an example of a line through the origin, which passes at some point through a lattice point. So via the identification we are considering, as you can see, this portion of the line here, well, it is equivalent to this portion here. So we can think of this portion as this portion on the torus. In the same way, this portion here is equivalent, the points in this portion here are equivalent to the points in this portion here, and these points here are equivalent to those here. So at the end of the day, since your line passes through this rational point, so this point with rational coordinates, it will close up on the torus. So you have to imagine that once you have performed these gluings, then you will end up with some closed curve inside here. So I can't draw it properly, but imagine some curve inside here that closes up at some point. This happens if and only if this line here eventually meets a point with rational coordinates. This is equivalent to say that the line has rational slope. So sorry, of integral coordinates, and this is equivalent to say that the line has rational slope. If the line has irrational slope, it won't meet any of these red points. So what it is going on is that you can draw it, it won't meet any of these points, and so you will end up with an infinite number of segments here. And so you will end up with a curve going through the torus without closing up. So this is the difference between the two situations. So in the first case, so when the curve closes up, what you get is an embedded subgroup of the torus. So is a kind of embedding of the real lines of the real numbers, thought as a Lie group inside the torus, and their image is a closed curve which is diffeomorphic to the circle. This is precisely this first part. In the second part, in the second case, what you will end up with is an infinite curve that won't close up. This is not an embedded submanifold of the torus, it is only immersed. It is only immersed, so it is not regular. And in any case, what you get is that the image H of this line inside the torus is an abstract subgroup of the torus. It is an immersed submanifold, and it is a Lie group. And so it is an example of a Lie subgroup of the torus. And again, if you want, you can think the immersion as this map here, if you prefer the representation of the torus as a product of two circles. So just take any real parameter in R. Its image in R2 will be the line through the origin with slope m, and then you will get an image inside the torus. So if this slope m is rational, the image will be an embedded submanifold diffeomorphic to S1. If this slope is irrational, then you will get a curve that won't close up. And of course, we have two different homologies in this case. In fact, here it is nice also to understand better which is the difference between the induced topology and the subspace topology. As you remember, once you have a map which is an injective map, and so by injection into the image, which is the map that, if you want, sends the line here in R2 inside its image here, then you can give to the image both the topology induced by the map, and you just declare a subset here to be open if it is the image of an open subset here, or you can give the image here the topology which is induced by the ambient space. This means that an open set will be the intersection of an open set of your ambient space with the subset you are considering. And you can appreciate it in this example here. Because in the first case, so now this is just a partial picture, so this is the torus, this will be the torus after the identification of the sides. So imagine this as having infinite segments, so that if you zoom, again, you will see other infinite segments, so they won't end up in any case, because this curve won't close up on the torus. So if you consider the inclusion given by this map F, well, then you can define a subset here to be open if it is the image by means of F of an open subset in the real line here. So you take an open interval inside this line and you pick its image by means of F here, and you will declare this to be open. This is the induced topology by the map F. Here, instead, we have the subspace topology. So you see this H, the subset H, as a subset of the torus. And so you take an open subset of the torus, which means an open subset, like for instance this one. This is just one special case, one special example you can see. And you declare a subset of H to be open if it is the intersection of H with an open subset of the torus. So what happens here is that now you have infinitely many intervals. And this is because, as I said, if you imagine to zoom this picture, then you will get another pattern like this one, so with other segments that continue that are really close but do not meet at any time. So as you can see, there is a difference between these two types of open sets. In particular, as you remember, if you consider an open set, then the union of open sets is open. And so in particular, the open set you obtain in this way is in particular an open set also with respect to this topology, because it can be described as the union of intervals. And every interval is open with respect to the induced topology. The converse is not true. So in particular, the induced topology, if you want, has less open sets. Instead, if compared with the subspace topology has less open sets if compared to the induced topology. And so this is the conclusion. So every open set in the subspace topology is also open in the induced topology, and this is because you can obtain such an open set by the union of infinitely many of these sets here, but the converse does not hold. So we have different topologies, and this is a nice example when one can appreciate this difference, the difference of the two topologies one can put on a subset of a manifold. Okay, let's move on. So we have some results that allow us determining when some subset is a Lie subgroup, and in particular, one result is this proposition saying that if you have an abstract subgroup of a Lie group, which just means that it is a subgroup in the algebraic sense, which is also a regular submanifold of the Lie group, then it is a Lie subgroup. So we are requiring here a stronger condition rather than the immersed condition. We are requiring that it is a regular submanifold. So we are requiring that it is both an abstract subgroup and the image of an Ebendig, if you want. So once these two hypotheses are satisfied, you have for free that your subset is a Lie subgroup of the Lie group. In fact, the idea is precisely this one. So a regular submanifold is the image of an embedding. You saw this last time. So if you consider the multiplication map, then in particular you can restrict it both to H cross. You can restrict it to H cross H. You will get a smooth map by composing the immersion of H cross H inside G cross G and the multiplication map. This is a smooth map, and now you use that H is a regular submanifold. So as you saw last time, this allows you to conclude that the image, since the image of this map is actually inside H, and since H is a regular submanifold, then this map induces a smooth map from H cross H to H, and so the multiplication is smooth. So pay attention to the fact that we can do this only because, so we can restrict the codomain of this map to H and get a smooth map only because H is a regular submanifold. So we can't do that if H is only immersed. And the smoothness of the inverse is proved in a similar way. So this tells you in particular that if you have an abstract subgroup and a regular submanifold, then you get a Lie subgroup. Of course, the regular submanifold condition, I repeat this once again, is stronger than the immersed submanifold condition. So by definition, a subgroup, as in this proposition, so which is both an abstract subgroup and a regular submanifold, is what is called an embedded Lie subgroup. So it is not only immersed. So it is a stronger condition than the definition of Lie subgroup. And we shall see later why a Lie subgroup is defined only as an immersed submanifold and not as an embedded submanifold. So in particular, the examples we examined before, so the special linear group, the orthogonal group, are both regular submanifolds of the general linear group, and they are also abstract subgroups. So they satisfy the hypothesis of this proposition. And so we had for free that they are embedded Lie subgroups of the Lie group, GL and R. Now there is another crucial result in the theory of Lie groups that requires actually much more information and much more techniques to be proved. And so here there is only the statement, and involves the so-called closed subgroups of a Lie group. Again, remember that a Lie group is a manifold, it has a topology, and so it makes sense to talk about open subsets, such as the general linear group inside the group of matrices. And it also makes sense to talk about closed subsets in the topology. So this really powerful result tells you that if you have a Lie group, then you can consider an abstract subgroup that is closed, meaning that it is closed in the topology of G, and you have for free that it is an embedded Lie subgroup. So this is a theorem that it is not proved, and it tells you that if you have a subgroup, so an algebraic group of an algebraic subgroup of a Lie group, which is also a closed subset in the topology of the Lie group, then it is immediately an embedded Lie subgroup. So in particular, it is a Lie subgroup according to the definition we gave before. Actually, it is much more nice because it is embedded, and so it has the topology induced by the Lie group we are considering. And here, for instance, if you want to see a proof of this one, if you're interested in it, you can find it, for instance, in the book by Lie I mentioned before, so Introduction to Smooth Manifolds. But be aware of the fact that you will need much more material. You will need to study much more material before being able to prove this theorem. But of course, one can use it. So, and it is really powerful because it is, you have just to check two really simple conditions usually. The first one is that it is closed in the topology, subset that is closed in the topology. And the second one is the algebraic condition that the subset is a subgroup. And here we have some examples related to this last part. So the first example is that the line with irrational slope in the torus we discussed before is not a closed subgroup, but what one can show is that it is dense. It means that its closure coincides with the torus. And on the other hand, the special linear group, the orthogonal group, you can describe them as zero sets of polynomial equations on the general linear group. Being the zero sets of polynomial equations, they are closed subgroups, they are closed subsets of GLN. And this is because, again, polynomial equations are continuous, and the preimages of continuous functions are of closed set under continuous functions are closed subsets. And so in this case, you have that both SLN, R, and ON are closed subsets of the general linear group. They are abstract subgroups. You can show it directly, here using the properties of the determinant, here using the definition of the orthogonal group. And so in particular, they satisfy the hypothesis of the closed subgroup theorem. And so you have for free from this theorem here, without making any further computation, that they are embeddedly subgroups of the general linear group. Now, there is this part now that deals with the matrix exponential. And it has, if you want, something to do, or say it has a lot to do with analysis and functional analysis, if you want, because it involves norm vector spaces, it involves a series of matrices in this case. So let's recall the definitions and properties that are useful for us, because the final aim of this section is explained in these first lines. So if we have a subgroup of the general linear group, sometimes we would like to compute the differential of a map on a subgroup of this group. To do this, as we saw earlier, as you saw last time, the best thing one might do is to consider a curve through the subgroup with a given tangent vector at a given point. And in this case, you can compute the differential of a map just considering the map evaluated at that curve, taking the derivative and evaluate the derivative at time equal to 0. We did an exercise like this one earlier. And so what happens here is that the matrix exponential gives you always a non-singular matrix and allows you to obtain a curve of non-singular matrices. So it allows you to obtain a curve inside this group here. So to define it, you will need this data. So we have to start with a vector space with a norm. And I will move briefly here. Let's see this briefly. This should be some well-known notions. So you have a norm, which is a function on the vector space, which satisfies these three requirements. So it is positive definite and vanishes if and only if the vector is 0. It satisfies this homogeneity condition, and it satisfies this triangular inequality, which is the so-called subadditivity. So this is what you call a norm vector space. And for instance, the space of squared matrices, which is canonically isomorphic to the vector space R to the n squared, can be given, so this space you can give the Euclidean norm, which is just the sum of the squares of the entries of the matrix, and then you take the square root of this sum. This is a norm, so it satisfies all these requirements. And how do you define the exponential of a matrix, of a squared matrix? Well, you consider this infinite sum of matrices. So this is a kind of series of matrices. So you start with the identity, then you consider the X matrix, then you consider the second power of X, and you multiply for this coefficient and so on. So you have an infinite sum of matrices. This is the analog of the definition of the exponential of a real number, if you want, so of the exponential function. We are doing this for matrices. Of course, when you define something as an infinite sum, you have to prove that this infinite sum converges to something that belongs to the space you started with. So we would like to show that this is actually a matrix. This is our aim now, because for the moment this is just a definition. And actually you can show this with some work. So first of all, you recall what is a normed algebra. So recall that an algebra is a vector space when you can also multiply vectors in a suitable way. So where also an operation multiplication of vectors is defined. And so for instance, the space of matrices is an algebra, the space of squared matrices, because you can multiply squared matrices, you can add them up, you can multiply numbers for matrices. So it is an algebra. It is normed because it satisfies the following requirement. So you say that an algebra is a normed algebra if it is a normed vector space, so you have a norm that is also an algebra and satisfies this inequality here. So its norm has to satisfy this inequality. Take two vectors, multiply them with the product operation you have on the vector space, on your algebra, take the norm, then the norm of this product has to be less or than or equal to the product of the norms. And what this proposition shows is that the matrix multiplication that one can define on the space of matrices makes the norm vector space R n times n with this norm here a normed algebra. So in particular, for any pair of squared matrices you consider, you have this inequality. And this is just a matter of computations in coordinates involving the Cauchy-Schwarz inequality for the scalar product, for the use of the scalar product you have on the vector space R n. So you just take the product of x and y squared, consider the ijth component, and you will end up with this object, which is, if you want, you can think of this as the scalar product of two vectors in a rank given by the by a line vector of x, capital X, and by a column vector of capital Y. So you use Cauchy-Schwarz here, you get this inequality, and then starting from this definition of the norm, of the square norm of the product, which is just the sum of all of these objects, you can get this inequality also here, and then manipulating the sums, you will end up with the product of the square norms. And so in this way, you show that the space of squared matrices with the norm defined before is a normed vector, is a normed algebra according to this definition. And now in a normed algebra, you have some results that you can show for convergence of sequences and of series. These are results, if you want, from that are similar to results that you already met in analysis. And so in particular, this tells you that if you have a normed algebra, take any element, any vector in V, take any sequence in V that converges to S, then as a consequence of this convergence, you have that the sequence given by multiplying the element A by every element of the sequence converges to the product of A and S. And similarly, if you have a convergent series inside your vectors, your algebra V, and you take any element in V, then the product of this element by this infinite sum of elements is the same as the infinite sum of the products of the single elements. So it's kind of distributive property in this case. And I wrote the proof of this proposition in this second part. I won't discuss it, but if you want, you will find it if you want to see it and read it and understand it. We will use this proposition later. So in particular, now to conclude, so now let's recall our final aim is to show that the series defined in this way converges. So if we can prove this, we have a well-defined matrix in this space given by this exponential of the matrix. And one can show this using these results. So first of all, if you have a series in a normed vector space, then you say that it converges absolutely if the real series of the norms converges in R. So this is a convergence as a series of real elements. So this is calculus 1 if you want. And recall that a normed vector space is said to be complete if every Cauchy sequence in V converges to a point in V. Again, I recall that what is a Cauchy sequence? Well, you have a sequence inside your vector space, inside your algebra V. You call it a Cauchy sequence if for each epsilon positive, there exists some natural number and naught, such that for each natural numbers m and n greater than n naught, you have that the norm of the difference between the term Sm and the term Sn of the sequence is bounded above by epsilon. This is the definition of Cauchy sequence, which is the analog of the definition of Cauchy sequence that you can give on real numbers for real sequences. So in the case of a normed vector space, you can define what is a Cauchy sequence, and you will call the normed vector space complete if every Cauchy sequence converges to a point, be careful, inside the same algebra. And for instance, what one can show is that the space of squared matrices with the norm we introduced before is a complete normed vector space. So in particular, every Cauchy sequence inside the space converges to a matrix inside the space. And in particular, one uses the fact that if you have a complete normed vector space, such as the space of matrices we are considering, then the absolute convergence implies the convergence. And why we prefer this, why it is nice? Because in this case, so in the case we are considering, the absolute convergence is a convergence for real series of real numbers. So we can use known results on real series to draw conclusions. So in particular, to show that a series of matrices converges, what it is now to show is that the real series of the norms of each element we are summing up is convergent. In particular, for matrices, you can use, for any real matrix which is squared, you can use the proposition we mentioned before, so this one here, saying that we have this property for the norms, to conclude that the norm of the kth power of a matrix is bounded by the kth power of the norm of the matrix. This tells you that if you consider the series given by the norms of the summands we were considering when we defined e to the x, which was, recall, 1 over k factorial x to the power of k. So you consider the norms of the summands, you consider the series, which is now a series of real numbers, then what you can use is this inequality here to show that this series is bounded term by term by the absolute value of this convergent series. You have that the first term in this sum is the identity matrix, its norm is just the square root of n. Then you will have the norm of x, you will have 1 over 2 factorial the norm of x squared, and so on. So you have that this series is less or equal than the sum, and this is precisely the square root of n minus 1 plus the exponential of the norm of x. This is a real number, and so this is just the usual exponential of real numbers. This is convergent, so this tells you that this series is bounded above by finite numbers, so this series is convergent, and so for free you have that also this series is convergent, and it converges to a matrix inside R n times n. So you use these results from analysis if you want to show that in this way, considering this infinite sum of powers of matrices, you will end up again with a matrix. So here you will find the proof of the proposition, and you will receive the PDF of this presentation later in the next days, I think. Well, now we have this exponential of matrices. It is defined in a similar way as it was defined in the case of real numbers. But pay attention to the fact that not all the properties that you have in the case of the exponential of real numbers hold also in this case. For instance, it is not true that if you consider the exponential of the sum of two matrices, you will get the product of the exponentials. And here you have a counterexample. For instance, taking these two matrices here, you make some computation and you show that these two are different. And moreover, you can show that this actually holds if the two matrices commute. And this is because if they commute, then you can use the usual sum, the usual expression for the kth power of the sum using this expansion, which is the usual expansion you already see in algebra for the kth power of a sum of real numbers. Of course, you have such an equality if and only if, if these two matrices commute. Otherwise, you can't use this. Using this, you will end up showing that in such a case, so under this hypothesis, the product of the exponentials is the exponential of the sum of the matrices. And moreover, we have this result, which is what we need. You can consider the exponential of a matrix times real parameter t. You can differentiate it, and the derivative is similar to the derivative of the usual exponential. You will get x, the product of the matrix x, times the exponential of the matrix dx. And you can do this product in both sides. Here, the crucial point is that we have a power series in T, and so we can differentiate term by term, since the series is convergent. So you start with this derivative, take the derivative term by term, so you just take the derivative with respect to T, and you will end up with an expression like this one. Now you can collect x and get precisely what we say. So x times this infinite sum, which is precisely e to the exponential of the matrix dx. And you can do this both collecting x on the left and both collecting x on the right. Okay, so and then you can also define everything we said here also when the matrix is a complex matrix and not a real matrix. Then there is the definition of the trace of a matrix, and I think you are familiar with this one. It's just the sum of the elements in the diagonal of the squared matrix you are considering. And the trace of a product of two matrices is the same if you exchange the two elements in the product, even if the product is not commutative. And moreover, if you consider the trace of a matrix of this form, where A is an invertible matrix, then the trace is the same as the trace of the matrix you started with. So these are common properties of the trace of a squared matrix. And here there is a proof, which is really simple. It's just a computation in coordinates. So now we would like to compute, at the end of the day, we want to show that the exponential we defined in this way as a power series of matrices is actually non-singular. So we want to show that its determinant is different from zero. So this is our aim now. So it will be, so in such a way we show that in particular an expression like this one, so the exponential of t times x will be a line of matrices in the general linear group. To show that, one uses the eigenvalues theory, and I recall you that the eigenvalues of a matrix are the roots of the polynomial equation defined in this way. And if we consider the field of complex numbers, we know that every polynomial has necessarily n roots counted with multiplicity. So working on the space, on the field of complex numbers, we know that we always have n solutions to this equation. And moreover, these are facts from linear algebra. First of all, we have that two similar matrices, so two matrices that are related by this identity, have the same eigenvalues, and this is because they have the same characteristic polynomial. So this determinant and this determinant are the same because of the properties of the determinant. And moreover, the eigenvalues of a triangular matrix, which means that you have a matrix, in this case, which is upper triangular, so you have some elements in the diagonal and 0 in the part which is down to the, with respect to the diagonal, which is below to the diagonal, sorry, then the eigenvalues of such a matrix are the diagonal entries. And this is because the determinant of this polynomial is precise, of this matrix here is precisely this product here. So the crucial point here is this result from linear algebra that tells you that any complex square matrix can be triangularized. This means that there exists a singular complex matrix A for which AX, A minus 1 is upper triangular, so as this shape here. And of course, and so in particular, the eigenvalues are precisely the entries you see in the diagonal. Of course, you can repeat this also over the real numbers because a real matrix can be viewed as a complex matrix. Also, in this case, it can be triangularized. The difference would be that A will be a complex matrix. So this will be, you will get a complex matrix instead of a real matrix. But we just need this fact here that every matrix can be triangularized to conclude, because first of all, you should know this very well, the trace of a matrix is equal to the sum of its complex eigenvalues, so we will skip this proof. And then here we are. If you consider the determinant of the matrix exponential of a matrix X, then it is equal to the exponential of the trace of X. So the trace of X is a real number, and so this one is the usual exponential you consider, so taking the exponential of the number E, you take the power given by the trace of X. So how to show this? First of all, you assume that X is upper triangular, then this power series gives you this power series here, and in particular in the diagonal entries, as you can see, you have the power series defining the exponential of lambda 1, lambda 2 until lambda n. So you will have 0 below the diagonal, you will have something above the diagonal, and you will have the real exponential on the diagonal. So the determinant of the matrix exponential of X will be the product of the diagonal elements of this matrix, since it is upper triangular. But the product of the diagonal elements is precisely the exponential of the sum of the eigenvalues, and so it is the exponential of the trace. And again, if you have a general matrix, you obtain the same result by triangularizing it. And so by similar computations, you arrive at the conclusion. Pay attention to the fact that here at some point you have to use this result that was given as an exercise before. So you have to use that. You can multiply term by term a convergent series. But in any case, this is what we need. The determinant of the exponential of a matrix is the exponential of the trace of the matrix. And so in particular, this tells us that the matrix exponential is always non-singular. This is because the exponential of a real number is never 0. So at the end of the day, we have obtained a curve of matrices inside the general linear group. And in particular, this allows us to consider curved matrices which start at any point we want with any tangent vector we want. So for instance, in this case, the power series of the matrix Tx at time equal to 0 is the identity, and its derivative using the property of the derivation we proved before is precisely, as you can see from here, x times e to the 0 matrix, and so it is precisely x. And so we have a curve passing through the identity with tangent vector, which is precisely x. And if you want to change the starting point, just multiply this exponential with the matrix you want. In such a case, you will get a curve starting at A with the tangent vector AX. And so in particular, you can compute the differential of the determinant at identity, and this is useful, for instance, to the computations we are going to do, And in particular, the determinant is a map from the general linear group to R, so its differential will be a linear map from the tangent space to the general linear group at the identity. It is isomorphic to the space of matrices, to the tangent space of R at 1, which is just isomorphic to R, so the differential of the determinant map at the identity is a linear map from the matrices to R. And what you can show using this curve we have just introduced is that its differential at any matrix is the trace of the matrix. And this is just a computation, because you just have to consider a curve passing through the identity with tangent vector x. This is precisely the matrix exponential we introduced. Take the derivative of this, and you use the fact that the determinant of this exponential is the exponential of t times the trace of x. This is the derivative of the usual exponential function, and then you will end up with the trace of x. So this tells you which is the shape of the differential of the determinant at the identity. Here there is another way of showing that the matrix exponential converges using the fact that the series is a Cauchy sequence. The sequence you can consider by truncating the infinite sum, because it's a Cauchy sequence. And here again, there are I added some comments in this. Again, you have a product rule for matrix valued functions that tells you that if you multiply two matrix valued functions and you differentiate it, you have a kind of product rule of Leibniz rule for this derivative. And the idea is just to see how the product is defined, and so you will derive the usual product of real functions. Then maybe we'll skip this about the identity component of a Lie group that tells you just what is the identity component of a Lie group. You can consider a Lie group. You can consider the connected subgroup, a connected subset containing the identity, and then you can show that it is an open subset and also a subgroup of the Lie group. If you want an example, for instance, the orthogonal group as the identity component, which is the special orthogonal group. So it is a subgroup containing the identity of the group. Here then there are some exercises you could try to do, but I think that I can skip this and then finally move to the last part, since there is not so much time. So let's define at least what the algebras are. So again, then of course you can see every comment here in the part when you will receive the PDF. So let's focus on a Lie group G. As we said before, if you consider an element in G, let's say small g in capital G, then the left multiplication is a diffeomorphism of the Lie group. We said this before, that it is smooth and its inverse is just the left multiplication by the inverse of the element G. So what it is going on here is that if you consider a neighborhood of the identity of the Lie group, then the left multiplication will map this neighborhood of the identity, so an open set containing the identity, inside an open set of the Lie group containing the element G. So in this sense, you see that the tangent space at the identity has some kind of special importance, because once you know what's going on near the identity, then using these depth multiplication maps, you will know what's going on in other points of your Lie group. And now we will see that one can give the tangent space at the identity a Lie bracket structure, so that it becomes a Lie algebra. And so in particular, you can define the structure of a Lie algebra on the tangent space of a Lie group. And it will be what we call the Lie algebra of the Lie group. That it is actually isomorphic to a special class of tangent vector fields to the Lie group. And it is what is contained in this last part, which is the canonical isomorphism between the tangent space at the identity and the vector space of left invariant vector fields on G. We will define all these notions now. So first of all, tangent space at the identity of a Lie group. As we said, left translation by an element of G is a diffeomorphism. So in particular, its differential is an isomorphism. Since this is diffeomorphism, it is an isomorphism of tangent spaces between, if you take the differential at the identity, it will be a diffeomorphism, an isomorphism between the tangent space of the Lie group at the identity to the tangent space of the Lie group at the element G. So all these tangent spaces are isomorphic. So in particular, this tells you that if you can describe the tangent space at the identity, then using the left multiplication, you will describe the tangent space at every point of the Lie group. Now, we have some computations of tangent spaces at the identity. For instance, for the tangent space of the general inner group at the identity, what you can show is that it is just isomorphic to the space of squared matrices. This is because the general inner group is an open subset here. And in particular, you saw this, I think, in the first lecture. You can identify the differential of the left translation with the left multiplication by matrices. So in this case, G is an element of G ln R, so it is a matrix, and the differential of the left multiplication by the matrix G is again the left multiplication by the matrix G. To compute the tangent space to the special inner group at identity, what you have to do is to consider a curve inside the special inner group starting at the identity with tangent vector, any tangent vector inside this space. We can always find such a curve if you want, using this proposition discussed in the first lecture. And since you find this curve, it is a curve inside the special inner group, so its determinant is 1. And now you can differentiate both sides. So if you differentiate this and evaluate the time equal to 0, well, you can recall the definition of the differential of the determinant map. And as you can see, you will end up with the differential of the determinant at the identity evaluated at the tangent vector to the curve you are considering. But we said before, just in the last part of the last section, that the differential of the determinant at the identity is just the trace of the matrix. So what's going on here is that the trace of the matrix we are considering in the tangent space here is 0. So what this tells us is that the tangent space to the special inner group at the identity is contained in the subspace of trace-free matrices inside inside the space of matrices. But this is a space, a vector space of dimension n squared minus 1, which is precisely the dimension of the special inner group. And so the two spaces must be equal, must coincide by results of linear algebra. So in particular, the tangent space to the special inner group at the identity is given by squared matrices whose trace is 0. In a similar way, you can compute the tangent space at the identity to the orthogonal group. In this case, you consider a curve in the orthogonal group starting at the identity and whose tangent vector is vector x, is a matrix x. Since this curve is in the orthogonal group, you have this relation here, so it's transpose times the curve equals the identity. Differentiate both sides, evaluate at t equals 0. So you differentiate, you get this by the chain rule we used before. Evaluate at t equals 0 and recall that c at 0 is the identity, and you will end up with this condition here, which tells you that the matrix has to be skew symmetric. So in particular, what you can show in a similar way as we did for the space of symmetric matrices, the space of skew symmetric matrices is a vector space whose dimension is precisely equal to the dimension of the orthogonal group, and so is equal to the dimension of its tangent space at any point. So in this case, what you show is that the tangent space to the orthogonal group at the identity is precisely the space of n times n skew symmetric matrices. So here there is an addendum I wrote that you can read later if you want, and gives you another way of proving this fact. So the fact that the tangent space at the identity of the orthogonal group is this space here, and that the tangent space at the identity to the special linear group is the other one we saw before. And probably Maurizio said something about this result in this last lecture. So I wrote here again the result one can use and the conclusion one can draw. And if you want, you can read this to add some information on these results. Let's move on now, and let's talk about left invariant vector fields on a Lie group. And let's see how they are related to the tangent space to the Lie group, to a Lie group at the identity. And this is why it was important, for instance, in the previous examples, to compute the tangent space to those matrix groups at the identity matrix. So now let's start considering a vector field on a Lie group. Let us assume that it is smooth. And as we said, left multiplication is a diffeomorphism. So as we said before, the push forward of the vector field X is well defined. And we say that a vector field is left invariant if it coincides with its push forward. So this means that if you consider any vector X at a point H belonging to this vector field, so you can consider the value of the vector field at H, consider the differential with respect to the left multiplication, then you will end up with the same vector, but of course evaluated at the point G times H, which is just the left multiplication of G and H. So this is what we call a left invariant vector field, a vector field that is sent to itself by the differential associated with the left multiplication. So if you want to use other words, X is left invariant if and only if it is LG related to itself according to the definition we gave earlier. So of course, a left invariant vector field is completely determined by its value at the identity, since once you know its value at the identity, you just apply the differential of the left multiplication and you obtain its value at any other point of the manifold. Conversely, if you have any tangent vector at the identity to the manifold, it induces a vector field, which is this A twiddle, in this case on G, just by means of left multiplication. So you just consider the tangent vector here and use the left multiplication map to define it in other points of the Lie group. In such a way, we obtain this vector field A twiddle, which is again a left invariant vector field. And you can show this just using the definition of the differential map. So just take the differential of the left multiplication by G, apply it to A twiddle evaluated at H, use the definition of A twiddle here, use the properties of the differential, use the fact that the composition of left multiplication is the left multiplication by the product of the two elements. And you will end up again with the vector field A twiddle. So in this way, you show that the vector field you define in this way is again left invariant. So you call such a vector field the left invariant vector field generated by the vector, the tangent vector to G at the identity. And now, if you denote by this symbol, capital LG, the vector space of all left invariant vector fields, then we get a one-to-one correspondence from this discussion here. Start from a tangent vector at the identity and extend it to a left invariant vector field A twiddle in the way we discussed here. Conversely, start with a left invariant vector field on the manifold and evaluate it at the identity to obtain a tangent vector at the identity. In this way, you get a bijection between the tangent space to the Lie group at the identity and the space of left invariant vector fields. It is actually linear. It is easy to show that such a map is linear. And in fact, since it is bijective, you will get that it is a vector space isomorphism. So this means, in particular, that the space, the vector space of left invariant vector fields on a Lie group, which is a subspace of the space of all vector fields on a Lie group, which is a smooth manifold. So you can consider tangent vectors also from that point of view. Well, the space of left invariant vector fields is finite dimensional. It's a finite dimensional vector space whose dimension is precisely the dimension of the group of the Lie group G, because it equals the dimension of the tangent space to G at the identity. So we have some vectors, some special vector fields on the Lie group, which constitute a finite dimensional vector space, whose dimension is precisely the dimension of the Lie group. This is what is the Lie algebra of the Lie group. So here there are some computations of left invariant vector fields. So for instance, on R, the left multiplication is just the sum from the left side of an element of R with another element of R, and then requiring that a vector field is left invariant tells you that it has actually to have constant coefficients. And so in particular, the left invariant vector fields on R are constant multiples of the vector field you can define on R using the standard coordinate. And in a similar way, you can show that left invariant vector fields on the general linear group are given in this way. So just identify the vector field with matrices, and these are given by, it is generated by the matrix, So if you consider a tangent vector at the identity, it can be identified in a natural way with a square matrix in G and R. And so you will get a correspondence in this way. So actually, I didn't say everything here because, of course, this A twiddle we define in this way is clearly a section of the tangent bundle to G. We have not proved that it is smooth, but actually it follows from this result here. This proposition tells you that every left invariant vector field on a Lie group is smooth. And to show this, just use left invariance and show that locally you can consider any consider any smooth function on the Lie group and show that if you apply your left invariant vector field to the function, then you get again a smooth function. And this is just a matter of rewriting this object here using shootable functions. So it is just a computation to prove this result, of course, using the hypothesis that the vector field is left invariant. Okay, so if I will skip this one and conclude. So from this proposition, so from the fact that every left invariant vector field is smooth, you get actually that the vector space of left invariant vector fields is a subspace of the space of all smooth vector fields of G. And in particular, if you have two left invariant vector fields, then also their Lie bracket is left invariant. And this is because since X and Y are left invariant, they are algebraically related to themselves. And if you remember the property we discussed earlier, this tells us that the bracket is also algebraically related to itself. So in particular, if you this tells us that if you start with a pair of left invariant vector fields on a Lie group and take the bracket, then the bracket will be again a left invariant vector field. And so in particular, the bracket will send a pair of left invariant vector fields to a left invariant vector field. And so in particular, the set, the vector space of left invariant vector fields on the Lie group has the structure of a Lie algebra. And this is what we call the Lie algebra associated with the Lie group. So in particular, here there is recall the definition of the algebra. So it's a vector space together with a bracket that satisfies the properties we discussed earlier. And of course, you can talk about Lie subalgebras, which are vector subspaces that are closed under the bracket. This means that you have a vector subspace, in this case, this Gothic H. And if you take the bracket of any two vectors inside H, you will end up with a vector inside H. If this happens, you call the subspace H a Lie subalgebra of the Lie algebra G. Now, this proposition 16.9, together with the definition of left invariant vector fields, tells us that the space of left invariant vector fields on a Lie group is closed under the bracket, and moreover, it is a Lie subalgebra of the Lie algebra of all smooth vector fields on the manifold. This is precisely what we call the Lie algebra of the Lie group. So this is the way in which we define a Lie algebra out of a Lie group. So now there are some results, again, that discuss the interplay between this presentation and this isomorphism between the tangent space to the Lie group at the identity and this Lie algebra of left invariant vector fields. In particular, let's say this really briefly since the time is almost over. So the fact here is that now we have a Lie algebra structure here. We do not have a Lie algebra structure here yet, but the idea is that using this isomorphism, you can translate the information here to information here, and in particular, give a Lie algebra structure also to the tangent space to the Lie group at the identity. In such a way, you will get what is called an isomorphism of Lie algebras, and you can interpret the Lie algebra of a Lie group equally as the Lie algebra generated by left invariant vector fields, or if you want, as the tangent vectors to the Lie group at the identity with a shootable bracket. And to define the bracket, you just use the left invariant vector fields induced by an element of the Lie algebra, by an element, of the tangent space to G at the identity. So the idea is that if you have to tangent vectors to G at the identity, then you will obtain two left invariant vector fields, A twiddle and B twiddle. You can compute the bracket, and so here we are moving in this side, and then you use this map to go back to the tangent space to G at the identity. So you define the bracket between two tangent vectors to G at the identity just as the bracket of the corresponding left invariant vector fields evaluated at the identity of the group. You can do this, and in such a way you obtain a Lie algebra structure also on the tangent space to G at the identity. And so you can also call the you can also define the Lie algebra of the Lie group to be the tangent space to G at the identity endowed with the bracket induced in this way, using left invariant vector fields associated with tangent vectors to the Lie group at the identity. Then you will find some computations, for instance, on the Lie bracket, on the Lie algebra of the general inner group. Now, the Lie algebra of the general inner group, as we say, it is just the tangent space to the general inner group at the identity, but the general inner group is open in the space of matrices, and so this will be nothing but the space as a vector space. This will be the space of n times n matrices, and after some computations you can show that the bracket defined on this Lie algebra, so on the Lie algebra of the general inner group, is nothing other than the bracket between matrices. So the bracket between tangent vectors at the identity to the general inner group is just the bracket between these two vectors seen as invertible matrices. So this is the result associated with this last proposition. And yeah, I won't have time to discuss this part, so I will skip this. And this just relates in some way the Lie algebra of a Lie subgroup of a Lie group with the Lie algebra of the Lie group. But as you may imagine, it will be a Lie subalgebra. And of course, one needs some work to show this. And so it's all this part here. And so in particular, let me move to this last part. So in particular, if you have, so the idea here is that if you have a Lie subgroup of a Lie group with an inclusion map, remember that this is an injective immersion. In particular, the differential is defined. It will be a linear map between the tangent space to H at the identity to the tangent space to G again at the identity, since it is a group homomorphism, so it will map the identity to the identity. And in particular, you can identify the tangent space, since such a map is injective. You can identify the tangent space to H at the identity with a subspace of the tangent space of G at the identity. And the bracket on this tangent space will be the restriction of the bracket that you can define on the tangent space to G at the identity in the way we said a few minutes ago. I said the restriction to this subspace. So in particular, the Lie algebra of a Lie subgroup may be identified with a Lie subalgebra of the Lie algebra of G. And finally, this is the final remark telling why when in the definition of a Lie subgroup, one does not require the subgroup to be embedded but only immersed as a submanifold. And the reason is the following. There is a theorem that you can find, for instance, in the book by Lie, that tells you that there is a one-to-one correspondence between connected Lie subgroups of a Lie group and the Lie subalgebra of its Lie algebra. Of course, this is really powerful because it tells you that once you consider the algebra, you consider any Lie subalgebra, and then you will end up with a unique connected Lie subgroup of the Lie group you are considering. If we remove if we consider a different definition of Lie subgroup, and we require it to be embedded instead of immersed, then this is not true anymore. Because, for instance, in the case of the torus, we saw that there were a lot of, let's say, Lie subgroups that were not embedded submanifolds. So, for instance, in the example of the torus, what it is going on is that the Lie algebra of the torus, of course, the torus is a Lie group, you can think of it as the product of the circle with itself. And you saw in the first lecture that, for instance, the circle is an example of a Lie group. So the torus is in particular a Lie group, and its Lie algebra is abelian. You can show that its Lie algebra is R2 with the trivial bracket. So with the bracket for which the bracket of any two pairs of vectors is 0. So the point is that the one-dimensional Lie subalgebras of the Lie algebra of the torus are the lines through the origin. And as we saw before, each line through the origin can be thought as a subgroup of R2 under the addition, and the image under the quotient map is a subgroup of the torus. And again, as we said before, if the line has rational slope, then the image is a regular submanifold of the torus. It will close up, you will get something which is diffeomorphic to the circle. But if the line has irrational slope, then the image will be an immersed submanifold of the torus, which is not embedded. And of course, this correspondence in this case works because every one-dimensional connected Lie subgroup of the torus is the image of the lines moving through the origin. And so this tells you why, if you want, maybe in some sense, to define a Lie subgroup as a subgroup, which is also a regular submanifold, so which is also an embedded submanifold, then you lose this property. You lose this one-to-one correspondence. And of course, this one-to-one correspondence is crucial if you want to let's say, work at the Lie algebra level and then move to the Lie group level, for instance. Of course, this and then again, here there are some other results and problems that you can try to think about, and you will find some solutions that I wrote and some further information. Of course, this is just the introductory part on the topic of Lie groups and the algebras. The story has much more information than what I told you here today. And because of course the study of Lie groups is closely related to the study of symmetries of manifolds, for instance. And so you can consider the so-called Lie groups of symmetries of a manifold, preserving some structure among the manifold. You will see, for instance, in the next lectures, how to compute lengths of curves on manifolds. So how to introduce a way of measuring lengths, measuring the angles between tangent vectors to the manifold. And this is done by introducing what is called a metric on the manifold. And for instance, you can consider transformations on the manifold preserving the metric, which are the so-called isometries of the manifold. So diffeomorphisms of the manifold preserving lengths of curves. And what it turns out is that the set of all these transformations has a topology. On this set, you can define a topology which gives it the structure of a Lie group. So this is only one instance, but in the general case, you can consider Lie groups as transformation groups of differentiable manifolds or spaces endowed with special structures. And so in some sense, as symmetry groups. Maybe, I don't know, maybe Maurizio will tell you something about this when he will talk about the Riemannian matrix in, probably not in the next lecture, but the one after that. Okay, I think that we can stop here, and there are some further interesting topics that one can study about Lie groups, in particular Lie group actions, and I will send you some material about this if you want to study it, to have some more information on this topic and on how Lie groups can be used to study symmetries of manifolds. Okay, I think we can stop here.
Thank you, Alberto.
Bye.
Thanks to everybody.
Ciao a tutti.
Bye.
Thank you.
Ciao a tutti.